Hello and welcome. My name is John Horvath, and my presentation today is about the use of subgrade modeling and models in foundation engineering. I've divided my presentation into several segments in order to present it in a logical fashion. I go through some basic concepts, the evolution of subgrade modeling and subgrade models, and end up with some mat foundation case histories. This is a fairly lengthy presentation, and you may find it convenient to watch it in segments. Well, let's start off with some basic thoughts as to how we got to where we are as a profession. We've all been there in our careers. You get involved with a project that involves a mat or raft foundation supporting a building, or perhaps a base slab of a cut and cover tunnel, base slab of a water resource structure, rigid pavement, slab on grade in a building. And the question that comes up very quickly is, what is the coefficient of subgrade reaction? Or perhaps it was called the modulus of subgrade reaction, or subgrade reaction modulus. Soil spring constant. Perhaps it was called a K value, or something with the name Winkler in it. But as I've said, we've all been there. For me, it was very early in my professional career. Long forgotten project. A supervisor came to me one day and said, "Here, find the soil spring constant for this site, this project." And I looked, and I looked, and I felt like I was Diogenes of Sinope, who walked around in daylight with a lamp looking for an honest man. And I continued to look for 6 years and eventually did some doctoral research and wrote a dissertation on the topic of subgrade models and modeling. So I've been looking at this topic for a long time, for certainly well over 40 years now. And I've come to the conclusion that on this issue of whatever you want to call it, soil spring constant, subgrade modulus, usually we give it the notation lowercase k, I've come to the conclusion that this parameter is to a very significant extent the unicorn of foundation engineering. It simply does not exist. So this then begs the question of, how did we get here as a profession? And what do we do about it? What do we do to resolve this strange dilemma of looking for a parameter that to a certain extent really doesn't exist? I believe the best approach to things is to always fix the problem, not worry about who created the problem, place blame for the problem, to fix the problem. And in a nutshell, that's what this presentation is all about. Show us how we as a profession got to where we are, and to present some what I feel are very practical, pragmatic ideas for resolving this issue. I want to start off with some basic terminology and notation. To begin with regard to what I call soil structure interaction, there are many types of structural elements that are in direct contact with the ground, and this could be a shallow foundation, deep foundation, some type of earth retaining structure, where the structural element is relatively flexible with respect to the ground. And we refer to the ground in these applications as the subgrade. The mat or raft foundation that I just showed you in the prologue is very typical of such structural elements. Problems that involve such relatively flexible structural elements are statically indeterminate, because in order to come up with an acceptable mathematical solution, you have to satisfy not only force and moment equilibrium, but also displacement and deformational compatibility between the structural element and the subgrade. These are what I call soil structure interaction problems, and I want to emphasize this broad definition of SSI because for some reason there are a number of authors who feel that soil structure interaction only applies to problems involving earthquakes and seismic loading. I don't accept this narrow definition. To me, soil structure interaction includes gravity as well as seismic loading. An essential element of soil structure interaction problems is that the force displacement relationship of the subgrade must be coupled with the force displacement relationship of the structural element. And if, as in the case of a mat-supported building, you have a superstructure, that has to be included in the equation as well. We have to consider the force displacement relationship of the structure and the structural members. So we have to consider the compatibility of these various force displacement relationships if we want to get an accurate solution to the overall problem. Because soil structure interaction problems require basic understanding of both structural and geotechnical concepts, it's useful, I feel, to review structural engineering concepts first. And I'm going to be limiting my discussion to those structural concepts that I feel are essential to the soil structure interaction problem. And while, of course, all of you who are listening to this presentation, you've all been educated in structural engineering, the problem is that, as we know, there is a diversity of terminology, notation, sign conventions that are used throughout the world. So really the purpose of this introductory comments on structural engineering is so that we establish the terms and notation, sign conventions that I'm going to be using throughout this presentation. So this next segment will deal with these structural engineering concepts that, as I said, I feel are essential to understanding soil structure interaction. Here's an outline of the topics I'm going to cover. And we'll start off with some overview comments. Foundation engineering is, of course, the area in civil engineering where geotechnical and structural engineers have to interact to produce a solution. And certainly soil structure interaction, that is the focus of this presentation, has historically been the greatest source of this interaction between geotechnical and structural engineers. One of the things that's interesting, I feel, about soil structure interaction is that it really is structural engineering that dominates and dictates what we do. It is the needs of structural engineering that have created the fundamental need for subgrade modeling in the first place. And also, it's the needs of structural engineering that dictates the type of subgrade models that are practical to use. And I emphasize practical. And geotechnical engineers certainly have a significant role because geotechnical engineers are responsible for quantifying these subgrade model parameters. As it turns out, as we'll see throughout this presentation, there are some concepts in structural engineering that really are essential to understanding subgrade models that we use. So as I said, because of this synergistic relationship of geotechnical and structural engineering in soil structure interaction problems, a brief review of basic concepts is in order, if for no other reason, to establish some common terminology, notation, etc. Now, in this primer on structural engineering, I'm going to be using one-dimensional flexure as a beam to illustrate the things I'm talking about. Please understand I'm doing this for simplicity. It's obviously presenting something in a two-dimensional medium, such as a narrated slideshow, if you will. It's easier to show things in 2 dimensions, which indicates one-dimensional flexure. But the concepts I'm presenting are readily extended to 2-dimensional flexure of a plate. Very important, we start off with sign conventions. Sign conventions used by geotechnical and structural engineers are quite different, as we know. First of all, the orientation of the coordinate axes. Really, the main difference is that geotechnical engineers call the vertical axis Z, or Z if you prefer. I do realize that most of the world refers to this letter as Z, not Z, as in here in the United States. And the Z-axis is positive downward, whereas structural engineers, it's the Y-axis is the vertical axis and is positive upward. I can't emphasize this enough. Believe me, although my education is primarily as a geotechnical engineer, I certainly have done a lot of foundation engineering and structural engineering in my career, and have been fooled many a time by the sign conventions of a piece of software I was using, until I realized, oh, this is a structural engineering program, and things are, in a sense, sign-wise, are different than geotechnical engineering. The other important difference is that in geotechnical engineering, it's compressive displacements, forces, and normal stresses that are positive. And that's because in geotechnical engineering, certainly on the ground, it's compressive stresses that dominate. It's just easier to make them positive. Where, of course, in structural sign convention, it is tensile displacements, forces, normal stresses that are positive. I'll also point out that it's quite common for geotechnical engineers to use an alternative notation for positive downward displacements, what we call settlements. The lowercase Greek letter rho is perhaps the most common alternative notation, especially in the older literature. I'm going to stick with W as the vertical displacement simply because when you're doing mathematical operations, taking derivatives, things like that, using the UVWXYZ notation simply is mathematically more logical. I do want to emphasize that the remainder of this presentation, including this segment where I'm talking about structural engineering concepts, is using a geotechnical sign convention. So for those of you viewing this presentation who are primarily structural engineers, please understand that the signs of stresses, things like that, will be opposite that which you're more familiar with. There's a number of topics in beam flexure I want to talk about, starting off with some basic definitions. Again, I point out using the geotechnical sign convention, allowing a beam to have a variable stiffness EI in the horizontal or X direction. Very frequently I will leave off the X or XY notation and just use the letter by itself, in this case W, to indicate settlement as the result of some applied load I call Q of X. Now, please don't misunderstand. This does not imply a uniform distributed load. This is just a stand-in for a load. You know, we can have a single point load. We can have multiple point loads. We can have any combination of loads. So this Q of X is just a stand-in for any type of loading applied normal to the in the downward direction on the top of the beam. We have a rotation, and again, throughout this presentation, I will be assuming the normal small displacements, which allow us to make an approximation of the arctan of dW dx. And also want to point out the radius of curvature of the deflected beam shape, because this will factor in some of the things I'm going to talk about later on with regard to subgrade modeling. The point being is that both rotation and, of course, bending moment, M, are proportional, in this case inversely, to the radius of curvature of the deflected beam shape. And this is a very important issue, especially with regard to the moment to recall. And finally, we have shear force. And please note that I will, in the derivations in general, because of the fact that EI is allowed to vary as a function of X, when when I'm taking derivatives, I allow for this variation in the formulation. I next want to talk about what we call simple beams. As we know, there are two theories for defining the flexure of a beam, subject to some transverse load Q of x and small deflections. The more basic one that's a staple of both civil engineering education and practice, and having been in academia for 33 years, I'm certainly very familiar with the education process of civil engineers, at least here in the United States. The most basic beam is what we call Euler-Bernoulli or simple beam, and the phrase you generally hear is that plane sections remain plane. And essentially what this does is to ignore the shear effects. All right, shear effects that occur under flexure cause the initially plane sections of a beam to warp, and that warping is neglected in simple beam theory. For plates where we have flexure in 2 dimensions, the comparable theory is what's called Kirchhoff-Love or thin plate theory. And here's the traditional differential equation of a beam. And certainly throughout my career, I've become a bigger and bigger fan of the matrix method in structural engineering, which, as you know, the matrix method is to structural engineering what the finite element method of a force displacement continuum is to geotechnical engineers. Geotechnical engineers like to break a continuum into 3-dimensional bricks, if you will. A structural engineer, she or he, likes to break a structure into sticks, if you will, and connect the sticks. Not to trivialize it, but certainly it's really the main difference between the matrix method and finite element method. The reason I like the matrix method is because the stiffness matrix, which is really the heart of the matrix method because it defines the unit displacements and rotations at each end of a structural element, really it provides a lot more insight, and we'll see this in the coming slides as opposed to the differential equation for some of these secondary factors that I'm going to talk about that are quite important to soil structure and around. So here's the formulation of a simple beam or a beam and bending in general. The stiffness matrix, we have the displacement vector, which contains the unknowns, and the load vector Q. And here's the stiffness matrix for an Euler-Bernoulli or simple beam. Again, keep in mind compression's positive, and L here is lowercase l is simply the length of the structural member. Well, let's talk about some of the complicating or secondary effects, starting off with shear effects. Shear effects are, of course, always present. You know, in engineering, just because we neglect something for simplicity doesn't mean it's going to disappear. Nature is not going to oblige us and disappear. It's still going to be there. So shear effects, of course, are always present. And the important thing about shear effects is they cause a beam to be less stiff and deflect more compared to simple beam theory. Now, of course, in a lot of applications, this reduction in stiffness and additional deflection is trivial. We ignore it, which is why simple beam theory continues to be the cornerstone of both education and practice. However, the reason I'm emphasizing it here is that for some foundation elements, and certainly this is true of mat foundations in general, shear effects can be important. And we don't want to neglect them because that overestimates mat stiffness, which is in general for a mat foundation, you don't want to overestimate the stiffness of the mat and the stiffness of the overall system flexibility. Certainly now with computer software, including shear effects and analysis is not a problem as it was in the past. And really, in my opinion, should be done so as a matter of course with dealing with mat foundations. Now, the Timoshenko beam theory, or what we call thick beam theory, relaxes the plane sections assumption. For plates, the comparable, what we call thick plate theory, is the Mindlin-Reissner theory. And here's the differential equation for Timoshenko beam theory. And you see the shear effects are the terms here that I've emphasized in red. And capital A sub B is what we call the shear area. The shear area, of course, is just the cross-sectional area of the structural member that contributes to the shear behavior. Now, if we look at it from a stiffness matrix perspective, here we see all the shear effects are reflected in this alpha sub V parameter here. And I've expanded on alpha sub V here, and you see again the shear area, which is 83% of the gross area for a rectangle. And I emphasize the rectangle because certainly for a mat foundation problem, that would be the shape that would apply. And we see here, because the shear effects tend to be, or all in, mostly in the denominator, they tend to make these terms smaller, which reduces the stiffness. That's why I say, in general, this really shows the power of the stiffness matrix concept, because when you see how making some change, in this case adding shear effects, it really kind of jumps out at you how those things affect the stiffness of the flexural member. I next want to talk about linear versus nonlinear behavior. Of course, historically, structural analyses were and still are to a very significant extent based on the original undeformed geometry of a structure. Now, we now refer to this formally as a linear analysis. Well, it's long been recognized that a linear analysis produces unconservative estimates of member loads under certain loading conditions where the deformed geometry of the structure actually increases the loads. Now, in the past, certainly when I was a student many years ago, this was referred to as the P delta effect, but is now more formally just called a nonlinear analysis. And really, the fixed end column is a classic example to illustrate this. In a linear model where you have an axial force P and a shear force V, go back here a second. The fixed end moment down here is simply V times the length of the column L. And the P only causes axial shortening of the column. In a nonlinear analysis, where we have the side sway delta, and this is where the P delta term comes in, we see that the fixed end moment now is not only V times L, but also is P times delta. So P provides a moment contribution in addition to causing axial shortening of the column. Really, the simplest way to understand the difference between a linear and nonlinear model is, in this case, the column will never buckle. I can recall many years ago looking at some early versions of commercially available structural analysis software, and which the basic module was based on linear model. And just running some simple problems, I was astounded. The column would never buckle. What's going on here? Well, I realized that was simply because the default version of the software only does a linear analysis. The column will never buckle, whereas, of course, in reality, buckling will occur for any column. Again, nonlinear effects are conceptually similar to shear effects in that they're always present. It's just that they may not always be significant, which is why certainly in routine practice we tend to ignore them. And certainly when you teach students basic structural engineering, you ignore the nonlinear effects. Well, again, commercially available structural analysis software, and you will hear me use this term time and time again throughout this presentation, commercially available structural analysis software. And the reason I do this is to emphasize that the things I'm trying to present in this presentation are not just some academician's pie in the sky theoretical work. Things that I will present in this in this presentation are practical. They're doable today. They were doable 10 years ago, 20 years ago. So that's why I'm emphasizing that the things I'm presenting are doable in structural analysis software that any engineer around the world can get access to. Now, the point is we could do nonlinear analyses these days, but yes, I do understand and appreciate that depending on the software package, this may be an additional cost for a nonlinear module, and it does take some additional effort on the part of the design professional involved. But nonlinear structural behavior has long been very, very important to soil structure interaction analyses, which is why I'm emphasizing nonlinear behavior so much. First and foremost, well before digital computers were available to civil engineers, and we'll see I'm going back to the 1950s here, there was a very interesting, I think, unique closed form solution of a beam column. Unfortunately, a beam column is, in my experience, a highly misunderstood structural element, and I'll elaborate more on that in a minute. Understanding the difference between linear and nonlinear analysis is really essential to what I'm trying to talk about here in terms of subgrade modeling and models. And I think by talking about what I call the true beam column problem, it's useful to highlight some of these differences between linear and nonlinear behavior. So the next topic I want to talk about is beam column. As I said, the beam column is what I feel is one of the most misunderstood structural concepts that I've come across. And that's why I emphasize what I call a true beam column. First and foremost, a beam column is not simply a beam subjected to both axial and transverse loads. Okay? You could have a beam subjected to axial and transverse loads and linear behavior, and all this axial load is going to do is cause shortening. A true beam column is really, it's actually a very unique problem in structural analysis because first and foremost, the governing differential equation is derived based on the deformed geometry of the beam. You know, the differential equations I showed you previously for a simple beam and the Timoshenko or shear beam, these are all based on the undeformed, non-deformed geometry of the beam. But in the beam column problem, you deform the beam in the problem setup, in the free body diagram that you create, so that this axial force creates a moment. So the uniqueness of what I call a true beam column problem is that it represents a nonlinear problem that can actually be solved in a closed form. You don't need any approximate, iterative, or computer solution. And as a result, it was certainly an attractive problem in the pre-computer era. The beam column was very, very attractive because it allowed you to rigorously analyze a nonlinear problem in a relatively simplistic closed form way. And what's interesting is that to a certain extent, I think geotechnical and foundation engineers have used the true beam column more than structural engineers. Certainly, if I look at the literature with which I'm most familiar, geotechnical and foundation engineering literature, I see geotechnical and foundation engineers using a beam column going back to the 1950s for a very wide variety of geostructural applications. This is a very nice report by the U.S. Army Corps of Engineers. It's in the public domain, of course. It can be found online in digital form. And it's nice because it's one of the earliest attempts to integrate the beam column, and in this case with a computer solution, but it also has worked examples showing a beam column used for a beam on a Fuss-Winkler subgrade, and I'll explain what this is subsequently. A laterally loaded pile and an anchored bulkhead. Now, is this the best way to analyze a laterally loaded pile? No, there's more specific software for this nowadays, but my point is this just illustrates the versatility of this. And by the way, I will emphasize, point out that this CBeam-C program, and for any of you who are former students of mine at Manhattan College, will certainly recognize this. I used the CBeam-C program for probably 20 years in academia as an instructional tool for both undergraduates and graduate students to give them some basic understanding of soil structure interaction. It was a very simple code, and as I said, it was a good instructional tool. It was in the public domain, so one could provide it to students at no cost. I do want to point out that the graphic that I used to illustrate the beginning of this presentation was taken from this publication. We see here in the application of a true beam column, it's really in the most basic form, it's an extension of Euler-Bernoulli or simple beam theory. And here's the additional term highlighted in red that the nonlinear beam column affects. Again, this is the moment caused by starting off with the deformed geometry of the beam. And you could have beam column effects in a Timoshenko or shear beam. And again, I think the stiffness matrix is the most powerful way to see how the beam column effects are incorporated. I've highlighted the additional term here. This is the simple beam stiffness matrix, just keeping it simple here. This is the additional term. Again, keep in mind that the axial forces are positive in compression. So from the stiffness matrix, it is apparent that a tensile force, which would be negative here, has the net effect of making the beam stiffer. All right? This is negative. This increases these coefficients, which is the same as increasing the stiffness of the beam. Again, you see why I like the stiffness matrix to illustrate some of these things. The effects of some of these things, in this case, axial load, really kind of jump out at you when you're looking at the stiffness matrix. And in compression, the axial force will cause a reduction in beam stiffness. These terms will decrease in magnitude. So then in the limit in compression, we see that when the axial force goes to 10 EI over L squared, this will cause some of the stiffness terms to become zero, which is really conceptually the equivalent to causing column buckling. And we see that numerically this compares favorably to the Euler buckling load, assuming we had a column with both ends were allowed to rotate, and the agreement between these terms would be better if we included shear effects. This does not include shear effects. I next want to talk about subgrade reaction. So we're slowly building on things here. We had a beam with transverse load. We added the axial loads. We now want to see what happens when the beam or beam column rests on material that provides a vertical reaction I call P of X along the underside of the beam. And again, this does not mean the P of X is uniform in magnitude and distribution. This is just a pictorial stand-in for a reaction that can vary in the X direction. Well, this P of X goes by a wide variety of terms in practice. You hear it called bearing stress, bearing pressure, contact stress, contact pressure. There's probably more terms we could think about. For historical reasons, I'm going to use the term subgrade reaction in this presentation. So subgrade reaction is simply the term I will use for the stress imparted on the underside of a structural element, in this case a beam. Now, of course, we can add the subgrade reaction to these various beam equations we've talked about, and you can see by highlighting in red the effect on a simple beam, a Timoshenko beam, a beam column without shear effects, a beam column with shear effects. And if we want to use the matrix method, the subgrade reaction appears as another known vector. And I emphasize known here because, as we'll see in the subsequent segments on subgrade modeling and subgrade models, the fact that P has to be known becomes quite important. So regardless of whether you use the differential equation or stiffness matrix, the primary takeaway I want at this point is to point out the subgrade reaction either has to be an explicitly known quantity or has to be expressible in terms of other known quantities. All right, so this is just emphasizing what I said a minute ago, and that is one way or another we have to be able to either know or define this subgrade reaction. And as we'll see, and I'm emphasizing this because as we'll see, this is really the heart of what goes on as subgrade modeling and how we choose subgrade models. These are fairly demanding requirements, and they certainly have influenced a lot of things. First of all, the evolution of subgrade modeling, as we'll see, and the development and, above all, retention of use of certain subgrade models. Why do we do things the way we do, going back to the prologue? Why have we been chasing this unicorn of a soil spring constant for all of these many, many decades now? And certainly how sometimes we've chosen to integrate subgrade models with beam and beam column behavior to achieve a single solution. The bottom line is that the entire subject of subgrade modeling and models as the focus of this presentation has been dictated by this need to either know the subgrade reaction explicitly or express it in terms of other problem parameters or quantities. And it has to be workable within the limitations of structural engineering. Again, this goes back to what I said earlier, that to a very significant extent, soil structure interaction analyses have been dictated by structural engineering. What can we do in structural engineering in terms of computational and solution tools? This has really shaped how we approach soil structure interaction problems. Not to trivialize the contribution of geotechnical engineers, but to a certain extent, we've kind of gone along for a ride. Structural engineers have said, look, this is what I can do, okay? This is what my analytical tools allow me to do. What can you, as a geotechnical engineer, do to quantify the parameters that I'm using? And this is really a classic example in civil engineering where pragmatic needs, I mean, what can we actually do in both practice and research, being more important than theoretical rigor. Well, having talked about beam flexure, and certainly in terms of the structural engineering concepts, these beam flexure concepts have been the primary thing I wanted to address. There are some secondary issues I want to touch on now because these do have an importance in soil structure interaction analyses. There are two issues with regard to Portland cement concrete that you should always consider when you're dealing with foundation elements and soil structure interaction problems. One is creep, and creep is really best reflected as a reduction in the apparent Young's modulus of the concrete in a soil structure interaction analysis. And a crack section. Crack section behavior can be significant and will cause a reduction in the section modulus. These effects are combined, and either alone or combined will cause a reduction in flexural stiffness. And again, this is a common theme I pointed out earlier, why we should include shear effects, for example, when we analyze a mat foundation. In general, the more flexible, for example, a mat foundation or a slab or some sort of structural element, the more displacement and deformation we will have to the overall structure. The point I'm trying to emphasize here is we do not want to emphasize the stiffness of the structural element, whether it's the mat foundation or slab or whatever. We want to consider shear effects, creep of the concrete, crack section behavior. We want to consider all the things that go into reducing the flexural stiffness of this foundation element, because we want to always analyze and design for the worst case scenario, realistic worst case scenario of this behavior. And I do want to emphasize that these two phenomena of creep and crack section behavior for Portland cement concrete, these are material phenomena. They're separate from, but they are additive to the shear effects, which are an analytical phenomenon. I next want to talk about the foundation element's self-weight. Another thing that you see talked about in textbooks and elsewhere is, for example, if I'm analyzing a mat foundation, do I include the self-weight of that mat foundation? And the answer is there is no single answer. There is no single guideline. It really depends on site and project specific factors. The subgrade condition, certainly if you're dealing with a fine grained soil where you have time dependent effects, you need to consider immediate loading versus long-term loading after consolidation or reconsolidation has occurred. And also changes in groundwater level, because very often the weight of the foundation element, a mat foundation, for example, will be used to resist groundwater pressures. I'll show you some case histories later on where this was a factor. The speed of construction, when do you build a superstructure relative to the mat? How long does it take for the mat concrete to cure? Things like that. And also loading conditions, especially when there's uplift loads from usually water pressure, but nowadays it might even be wind loads as well, or seismic loading. There's also separate consideration when you're talking about the effect of foundation weight on the foundation behavior, that is the actual flexure and bending moments in, say, the mat itself, or the superstructure behavior, whether we're talking about the deformation of the superstructure. I found the net result is on most projects, you really wind up looking at doing multiple analyses, both without and with foundation element weight. You need to consider different stages of construction and post-construction loading. So the answer, as I said, is there is no single answer. One way I found is flexible when you're doing an analysis is you input the foundation element as weightless, and then you can actually include the weight or remove it, add it, include it in a staged analysis as an equivalent distributed load as appropriate. This next segment moves on to what is the heart of this presentation, and that is how the need for subgrade modeling evolved in foundation engineering practice, where it's been, where it is at the present time. Here are the topics I will cover with some basic concepts and talking about where we have been in the past in the pre-computer era and where we are in the present and might want to be going to in the future. The subgrade modeling draws on, it's really an incredibly multidisciplinary area that includes engineering, the applied sciences and mathematics, And the end goal of all subgrade modeling is to create a very application-specific constitutive model, and we call that a subgrade model. And this subgrade model of a continuum, the most significant thing about subgrade models as a constitutive model is that it eliminates one dimension of the actual continuum that's under consideration. So the most general three-dimensional continuum that would, say, be under a mat foundation is expressed as a two-dimensional subgrade model. A two-dimensional continuum, such as you might have with, say, laterally loaded piles, is expressed as a one-dimensional subgrade model. And in all cases, the resulting mathematical model, the subgrade model, is applied only to the surface of the continuum. And the reason we do this is solely for analytical simplicity. I mean, no one will dispute that a true three-dimensional constitutive model of soil, for example, is the optimum model to use. But we do subgrade modeling to eliminate one of these dimensions, really for analytical simplicity. Now, the subgrade models that have grown out of subgrade modeling is obviously related, but that is a separate topic that I'm going to discuss in the following segment of this presentation. So this presentation segment discusses the technical issues that created the need for subgrade modeling in the first place. Why did we have the need to eliminate one dimension from the continuum that's controlling the behavior of the structural element? Obviously, we had to do this for a reason. What were those reasons? The initial very limited intended use of subgrade modeling, and this is something that I think the vast majority of both practitioners and academicians at the current time and for many years have forgotten about. That subgrade modeling was developed initially for a very, very limited use. Actually, was a structural use, not geotechnical at all. And then talk about how subgrade modeling has expanded to be a much broader usage than it is at present time, much more general usage. And again, I'll continue to use the common example of a mat or raft foundation supporting a building for this discussion, but it is representative of other foundation elements with a horizontal orientation, such as combined or continuous footings, a slab on grade, say in a building floor, the ground floor of a building, base slabs of cut and cover tunnels, base slabs of water resources structures, tanks and culverts, as well as so-called rigid pavements. And we can extend the concepts of subgrade modeling to other problems. Deep foundations, obviously, the laterally loaded pile problem. This was one of the earliest uses of subgrade modeling going back to the 1950s and the demands of the then very new offshore petroleum industry, as well as flexible earth retaining structures, cantilever walls, sheet pile bulkheads, things like that, anchored bulkheads. So as I said, the exemplar application of a mat foundation is used in the remainder of this presentation. And using this three-dimensional picture, really the goal is to eliminate the Z or Z dimension from analytical consideration. And again, I point out I'm going to be using the geotechnical sign convention. And also I have placed the origin of the coordinate axes at foundation level, the top of the subgrade. And really that's for convenience to facilitate discussion of subgrade models in the following segment. Now again, for simplicity, I'm only going to be looking at a two-dimensional problem. That's simply for simplicity in presentation. I've eliminated the third dimension just for simplicity. So everything I'm talking about is completely general and can easily be extended to the true three-dimensional problem behavior. Some background. If we step back and think about this problem, what I call the ideal analysis, the ideal way to analyze this problem would be consider the three components. We have the building superstructure, we have the mat foundation, and we have the subgrade, which is probably soil, but it could be some other materials, as we'll see in some case histories, would be to solve these in a single piece of computer software. So you would have a hybrid matrix method, finite element method solution, right? You would decompose your superstructure and mat using matrix method concepts of structural engineering. You would have three-dimensional bricks of a finite element model to handle the geotechnical parts. And you would use state-of-art constitutive models for each problem component. So you can analyze each component as accurately as we can at the present time. Now, in principle, this is achievable nowadays. We certainly have the mathematics for it. We could write the computer software for it. The software would, in and of itself, not be a problem. And at least in principle, you have the computer hardware for it. Although you would need, obviously, a pretty substantial computer because the size of the combined stiffness matrix, the number of unknowns, would be substantial, to put it mildly. But there are very significant pragmatic constraints for doing this ideal analysis. To the best of my knowledge, does a piece of software exist nowadays that you could do a state-of-art matrix analysis of superstructure and mat and state-of-art analysis of the subgrade? Most commercial software, which is structures oriented, could not do that. It just does not have the geotechnical, the many different geotechnical models one would like to see. I'm familiar with the Diana software, somewhat familiar with Plaxis 3D. These are predominantly, or I would say nominally, geotechnical programs that have very good structural capability, at least for certain structural components. But I think it's a fair statement to say that this ideal piece of software does not exist at the present time, although it certainly could be written. You would certainly need a team of design professionals with expertise in both structures and geotechnical engineering to create the model and determine material properties. And although I wouldn't want to hazard a guess as for execution time, it would likely be substantial, quite possibly in the realm of days. And that's just for one analysis, at least with the hardware that most practitioners would have access to. And I think this would be impractical for routine design. In design, you have to look at many different design variations. You're constantly tinkering with the components. And for each component, you're looking at many different load cases. So the point I'm trying to get at here, this ideal analysis, could we do it nowadays? Yeah, in principle. Is it a realistic expectation? No, I don't think so. Now, I do want to point out that in this presentation, notice I put the top of the mat flush with the ground surface. That's just for simplicity. We could have all the basement levels you want. So I don't want you to think that what I'm talking about is limited to what I've shown you here. This is just a simplistic idealization of things to talk about the key concepts. But in this ideal analysis, the one thing I do want to highlight is that the contact surface between the mat and the subgrade, all right, the underside of the mat, the top of the subgrade, what we refer to colloquially as foundation level. Notice that this planar interface is entirely within the ideal model that I'm talking about here. Consequently, any of the stresses and displacements we would calculate at the nodes along this interface, they would all be calculated outcomes from this ideal analysis. You wouldn't have to make any special assumptions or inputs to deal with what is going on at this interface. Now, the reason I'm emphasizing this will become very clear in a minute, okay? But I do want to point out that in the ideal world, you don't have to make any special assumptions or whatever as to what's going on here. This would just be some calculated results at nodes in who knows how many hundreds of thousands of nodes within this overall model. I next want to talk about the subgrade reaction, which is again the stress or pressure acting at the underside of a foundation. So, of the many calculated outcomes from this ideal analysis that we might perform, geotechnically, probably the only thing of primary significance would be the magnitude and distribution of settlements. Of course, the structural engineers, they would be concerned about the member forces in the superstructure, the moments, things like that in the mat. But from a geotechnical perspective, we'd be most interested in the settlements because certainly we would be interested in the differential settlements of the mat and the superstructure, as well as rigid body rotation. Realistically, you know, with high-rise buildings, if you resolve all the forces down to foundation level, they will not be concentric with the foundation, with the mat, the geometric centroid of the mat. You're going to have some offset. So there's always that potential for rigid body rotation of the superstructure, which obviously in a high-rise building becomes a concern because a certain angular distortion, the magnitude of lateral displacements will increase with increasing height. I also want to point out that these settlements, W, X, Y, will extend beyond the edges of the mat. You're going to get settlements, of course, outside the limits of the structure. I think of less importance would be the subgrade reaction acting along the underside of the mat. And that's simply because bearing capacity rarely governs mat-supported structures. That would be the only reason you would be interested in these subgrade reaction, these bearing stresses, would be for bearing capacity. I next want to talk about a parameter that I will call the coefficient of subgrade reaction. And again, we're still talking about this ideal analysis. Of relevance is that if you look to some arbitrary point I along the foundation level, this interface between the mat and the subgrade, you would obviously have a settlement at that point, W sub I, and you would have a subgrade reaction, P sub I. And we can define an arbitrary parameter that I will call the coefficient of subgrade reaction, CSR. At that point would just be the ratio of P of I to W of I. And the coefficient of subgrade reaction, and again, this is the parameter I mentioned qualitatively at the beginning of my presentation, prologue. This would be a parameter that a lot of people would call modulus of subgrade reaction. I call it a coefficient because it has dimensions of force per length cubed. Modulus in general has units of force per length squared. So this is not a modulus in the traditional definition. But for reasons we'll see, these dimensions are better visualized as force per length squared. I cannot emphasize too much that this coefficient of subgrade reaction is, first of all, it's an arbitrary and arbitrarily defined parameter. I mean, I could call this ratio of subgrade reaction, calculated subgrade reaction to calculated settlement in this ideal analysis. I could call it anything I want. So this term is certainly arbitrary. And again, I emphasize these are calculated results. At least in this perfect world where I'm analyzing superstructure, mass, subgrade together, this coefficient of subgrade reaction, if I felt compelled to define it, it'd be easy. These are both calculations, so this is just the calculated result of calculated results. I think it's pretty obvious that this coefficient of subgrade reaction is a very complex function of the superstructure, the mat, the subgrade, and also very specific loading. Right? If you had a different load case on this system, and again with the superstructure, you'd be looking at different combinations of dead load, live load, wind load, seismic, all sorts of things. This coefficient of subgrade reaction would be, not only would it be different at every point, it would be different for every load case for the same problem. Well, let's come back down to earth, come back down to reality. How we've talked about the ideal case. I think we've agreed it'd be nice to do. We simply can't do it with current technology. What did we do in the pre-computer era? That certainly is a good question. Well, although an ideal analysis would be a challenge at the present time, it was impossible before digital computers. So what did people do? Well, there were multiple strategies that were used, but they were all based on decomposition of this actual problem. 3 independent components. And there were very simplified assumptions about how these components interacted. Typically, the structural engineer would do an independent analysis of the superstructure, would neglect differential settlements, and you would get some reaction Q of XY. And again, Q, this is not meant to imply a uniform distributed load. These could be any number of varying column loads. So this is just a stand-in for variable loads at the base of the columns of this building, for example. And then you turn around and you take this Q of XY, and this would be now the applied load on the mat, and you would assume that there was some subgrade reaction PXY on this mat. Notice you'd have to assume this. And then you do a separate independent settlement analysis under some applied stress P prime of XY. And I want to emphasize here, these two subgrade reactions are not necessarily the same. All right? P of XY is the subgrade reaction on the mat. P prime of XY is a subgrade reaction used in the settlement analysis. These could have different magnitudes, certainly different distributions, and that was considered perfectly logical, perfectly acceptable in the pre-computer age. It's very important to understand this. And actually, I'll show you a couple case histories that at the end of this presentation that were initially done where this difference existed. Well, obviously, this approach involved many approximations. The most significant one, certainly from the viewpoint of this presentation, is that the subgrade reaction, which in an ideal analysis was simply one of countless calculated results, now has to be an essential known input parameter. And that's really a tectonic paradigm shift, that you're taking something that in the ideal world, in reality, is simply an observed result, and now you're forcing it to be a known input parameter. In my opinion, it's this paradigm shift with respect to subgrade reaction that created these long-standing challenges and really misunderstandings in soil structure and interaction analyses that persist to the present time. Remember in the prologue I said we have a problem? Well, this is the heart of the problem. We're forcing something that really is an observed calculated result to be a known input parameter. So really the remainder of this presentation is devoted to discussing how foundation engineers have dealt with this challenge, this inversion of calculated result becoming an input parameter in the past, in the present, and how I think we should deal with it in at least in the near term foreseeable future. The simplest way in the pre-computer era for forecasting the subgrade reaction was what I call the conventional method of static equilibrium, In books and publications, you'll see this referred to as the rigid method and a variety of other names. I call it the conventional method of static equilibrium. It's really a logical extension of the very simple approach we've historically used for footings. All right, for footings, we take the resultant force from a column and we apply the well-known P over A MC on I equation to develop an assumed subgrade reaction of bearing stress under the footing. Well, in the conventional method of static equilibrium, we do the same thing for mats. The more significant implication of the conventional method for mats is that the mat is assumed to be structurally rigid. And by the way, structurally rigid is not the same as geotechnically rigid. Geotechnically rigid implies that you get a stress distribution consistent with a structural member. We assume structural rigidity. By assuming that the mat is structurally rigid, the mat deformations don't have to be considered as part of the solution process. We're just using statics, and that's why I call it conventional method of static equilibrium. We get an assumed stress distribution on the underside of the mat based simply on satisfying force and moment equilibrium with the applied QXY. Well, this certainly made life easy in the pre-computer era because it renders the mat component as statically determinate. Well, the problem is that even relatively thick mats exhibit some flexibility. So the calculated moments you get from this conventional method of static equilibrium are going to be incorrect. Now, I've seen many generations of structural engineers, foundation engineers say, well, yeah, I know the rigid method, conventional method, the moments are too large, but they're conservative and safe. Right? These are the magic words in civil engineering, right? Conservative and safe. Who can argue with that? I've been in this profession for over 48 years now, and certainly conservatism and safety, that's part of what we do as civil engineers. But I've also seen a lot of bad engineering hide behind conservatism and safety. And let's be realistic about this. I'm not saying we should not be reasonably conservative and safe as civil engineers. That's part of what we get paid for. But we should not hide bad engineering behind conservatism and safety. Again, that's just my own opinion. I do want to point out that this argument is inherently flawed with respect to mats because with mat foundations, you typically have moments of both signs, both positive and negative. And if you simply do an analysis, you'll find that this conventional method or rigid method, whatever you want to call it, it may give you moments that are too large of one side, but they're too small of the other. So you're always going to be, at least for one side of the moments, you're going to be unconservative and potentially unsafe. So conservatism and safety is not a good excuse for using the conventional or rigid method. So let's look at the other alternative methodology that took mat flexibility into account. I cannot emphasize too much as we get into this. The sole purpose of doing this was to produce a more accurate estimate of bending moments within the mat. This alternative methodology, now I'm not going to talk about, had nothing to do with geotechnical engineering per se, nothing to do with settlements. It was strictly a structural engineering accommodation to allow engineers to get a better handle on the bending moments within the mat. Now, this alternative to the conventional or static method is based on the assumption that, again, you have a mat foundation, let's say, with some column loads, that this actual loading and the bending moments that develop from this actual loading can be decomposed into two components. And these two components are superpositional. So we're invoking elastic behavior and superposition here. First of all, you have what we call local bending moments. And local bending moments assume that these columns are far enough apart that the localized bending, and by the way, I've exaggerated this to make a point, this is where that radius of curvature of bending that I showed you early on, I said moments were proportional to 1 over the radius of curvature. So the sharper the radius of curvature, the larger the bending moment. So so-called local bending moments assume that these loads are spaced far enough apart. Right? The mat foundation might be 20 or 30 feet apart, right? 6 to 9 meters apart, something like that. But these loads are far enough apart so that whatever local bending you get is just due to that single point load from the column. So you have a whole bunch of these independent point loads, local bending moments, local flexure. And in addition, you're going to have what are called global bending moments, because all of these point loads will, as you go down in the subgrade, their effects will overlap and multiply in some cases, and you will get some stress deeper down in the subgrade, and typically this will produce the class of what we call dishing or sagging pattern of bending of, say, a mat foundation or slab or whatever. And these produce what we call global bending moments. Now notice, again, going back to this radius of curvature, that these local bending moments produce a sharp radius of curvature and therefore larger moments. And notice how with the global moments, you have a larger radius of curvature and therefore smaller moments. So the global bending moments tend to smooth out some of these local bending moments when you add them together. And I'm emphasizing this because, as we'll see, both in this segment as well as in the case histories, that in some cases engineers omit the global bending moments. And the reason they do that is actually, in many cases, from a structural perspective, somewhat conservative. But know that, as with the conventional method of static equilibrium, in this alternative method, the subgrade reaction, P of xy, must be known for calculating each moment. Right? And the subgrade reaction is actually a bigger challenge for the local bending moment than the global. And this is because for the local bending moments, you really must consider the flexural stiffness of the mat or the slab or whatever as a problem parameter. Well, this challenge was met by what you see most commonly called in literature the beam on elastic foundation problem. And in my opinion, this is unfortunately, one of the worst names of a problem anyone has ever dreamt up. It has to do with the word elastic. I have seen many, many, many engineers in both practice and academia who think that the word elastic here means that this is a theory of elasticity subgrade. It's not. The beam on elastic foundation problem has absolutely nothing to do with the theory of elasticity of the subgrade. Elastic is used here in a very colloquial fashion to mean something that is compressible or spongy or elastic. It's a colloquial word of the use of the word elastic. But unfortunately, beam on elastic foundation is a term that has been with us for the better part of 100 years. It's not going to go away anytime soon, if ever. So we're stuck with it. But we should at least understand what it really means. There was an entire monograph written in 1946 by Atani that dealt with the beam on elastic foundation problem. It's a classic. And he assumed that the coefficient of subgrade reaction, which is a necessary part of the beam on elastic foundation, could be used to define the subgrade behavior, but again, with a role reversal. All right? Atani and everybody since then has assumed that the coefficient of subgrade reaction was known. Right? Ideally, it is not known. It's, as I've shown here, it's a calculated outcome, but in the beam on elastic foundation problem is assumed to be a known input parameter. Right? So notice this role reversal. Ideally, this arbitrary parameter I call coefficient of subgrade reaction is a calculated result. That's the ratio of two calculated results. When we use the beam on elastic foundation solutions or something similar to that, this now becomes a known input parameter. We have to know this in order to be able to calculate settlements and the subgrade reaction P. And again, I keep emphasizing this because, in my opinion, it can't be emphasized enough. In the pre-computer era, one had to assume, no matter what analytical approach you use, you had to assume that you knew the subgrade reaction. One way or another, you had to assume that you knew it. It's important to understand that this simplistic assumption did not originate with Hattani. Depending on who you want to believe, it either originated with Fuss in 1801 or Winkler in 1867. Certainly in the English language literature, almost everybody attributes it to Winkler, but if you dig deep enough and if you want to believe certain publications, Fuss came up with this quite a bit earlier. I don't want to get involved into who discovered this. Throughout the remainder of this presentation, I refer to this as the Fuss-Winkler hypothesis. You can believe whomever you want invented it. It's up to you. Of course, the benefit of the Fuss-Winkler coefficient of subgrade reaction relationship is that it eliminates subgrade reaction as a problem parameter because it's linearly linked to settlement that is already a problem parameter. So if we stick this in the Euler-Bernoulli or simple beam on a subgrade, this equation, which we saw previously, becomes this. Now, there are many different notations for the coefficient of subgrade reaction. The lowercase letter k is the most common, as I indicated in the prologue. This is our mysterious term that we've been chasing after for decades. But I'm using the coefficient of subgrade reaction terminology here to really emphasize the link with the generic definition and the fact that coefficient of subgrade reaction is ideally and theoretically a calculated result. I'm not going to illustrate the implementation of this in a stiffness matrix. It's in just about every textbook you can find. However, the point I do want to emphasize is that the steep price that we pay for this analytical simplicity, being able to go from this to this and get rid of subgrade reaction as an explicit problem parameter, is that if you step back and think about it, what it means is that you need to know the answer, the coefficient of subgrade reaction beforehand, in order to calculate the correct answer, the coefficient of subgrade reaction. And if this sounds like a ridiculous example of circular logic, folks, it is. Okay? It is simply a statement of reality. This is the price we pay for being able to say, yeah, I know the subgrade reaction beforehand. When in reality, subgrade reaction is a calculated result from an ideal analysis. Now, that having been said, history has shown that in certain very narrow applications, and probably a classic one is the laterally loaded deep foundations application, we can actually satisfy this ridiculous requirement. I mean, this ridiculous requirement is really the heart of the PY method that we've been using since, what, the 1960s for laterally loaded piles, all kinds of deep foundations. With laterally loaded deep foundations, we've been running instrumented load tests since 1950s, 1960s. So we've created this massive database of answers that people have correlated with soil types. so that, yeah, we can forecast these PY curves, which are basically, we're forecasting the answer beforehand. But that's a very unique special situation where we've been able to do so many countless number of instrumented load tests on laterally loaded piles and drilled shafts and all sorts of deep foundations that we, in a sense, have gotten pretty good at knowing the answer beforehand so that we can calculate the correct answer on a project. But it is not true as a general statement. In general, for soil structure interaction problems, we cannot reasonably guess at the answer beforehand. Now, unfortunately, this has not stopped generations of foundation engineers from using this approach and having to guess the correct answer beforehand to calculate the correct answer. And in all fairness, it was certainly understandable and defensible in the pre-computer era, because what was the alternative? The conventional method of static equilibrium. So, you know, this approach, as I said, before digital computers, was certainly understandable. And now, really, the classic application of this concept of the beam on elastic foundation approach as an alternative to the conventional method of static equilibrium in the pre-computer era was published by Terzaghi. Now, Hitani's work was certainly seminal, but if you look at Hitani's work, it's all structural. The geotechnical aspect he gave some thought to, but it was really not usable. Terzaghi came along about a decade later, and Terzaghi's major contribution is he put some very sound geotechnical thinking to complement Hitani's work with the structural side of things. Now, to the present time, everybody knows about Terzaghi's 1955 paper in geotechnique. Right? You see it referenced in textbooks and manuals, things like that. Unfortunately, it is, in my opinion, really misinterpreted, misunderstood, and worst of all, it's misused with the passage of time. I'm going to go through some key points in detail. If you don't believe me, I suggest you go back and read Terzaghi's paper very carefully yourself. The point I'm getting at here is, as we'll see, Terzaghi was focused on a very narrow goal. And it seems for a few years after that, foundation engineers understood that. But for some reason, over time, and quite bluntly, I will blame textbooks. Having taught at the undergraduate level for over 30 years, I could tell you that at least in the typical textbooks that we've used in American engineering schools, a lot of these textbooks really do not properly present Terzaghi's work. You know, they show some of the end results, and I think have contributed to the misunderstanding of where we are now. Why, for decades, we've been chasing after this unicorn, as I said in the prologue. First and foremost, there's two elements to Terzaghi's work I need to emphasize. First of all, he used the beam on elastic foundation solutions solely for structural engineering goals to be able to estimate local bending moments. To a certain extent, Terzaghi's 1955 paper has nothing to do with geotechnical engineering. It uses geotechnical input, but it is solely for structural engineering goals. A better way to calculate moments as opposed to assuming structural rigidity. Terzaghi left it up to the end user to decide whether or not to include global bending moments in a problem. And I think one could make arguments. In some cases you may want to include them, other cases not. Terzaghi assumed that the coefficient of subgrade reaction, K value, if it makes you happy, in the Fuss-Winkler hypothesis was a constant value. It doesn't have to be. He assumed it was because most of Hitani's solutions were assumed a constant value. Terzaghi assumed that the coefficient of subgrade reaction was a function of several variables: soil type, the flexural stiffness of the foundation element. And this is why I said in the prologue that generations of foundation engineers chasing after trying to link coefficient of subgrade reaction to fundamental soil properties, it's been a waste of time and money, because it's a function of, yes, it's a function of soil type, but also a function of the foundation element in contact with it, as well as the load case. As I said earlier, you have the same problem, you vary the load case, you're going to get a different distribution of subgrade reaction. The other element of Terzaghis' work I want to emphasize relates to settlement. He left it up to the end user how to calculate settlements. Because Terzaghi clearly said, and I quote here, the theories of subgrade reaction should not be used for the purpose of estimating settlement or displacements. He said, don't believe me? Go read Terzaghi's 1955 paper yourself, and you will see this statement explicitly as I've quoted it. Again, Terzaghi saw the whole concept of assuming a, if you will, soil spring constant as a better way to estimate local bending moments. He said nothing about global bending moments. He said nothing about settlement. It was a very narrow structural application. And importantly, it meant that the settlements that you do get from a beam on an elastic foundation calculation for local bending moments never ever interpret as real settlements. And anyone who's ever used Terzaghi's magical values that you see in tables in every textbook I've ever seen is that the settlement magnitudes you get from using his method are typically at least an order of magnitude smaller, an order of magnitude. All right? If your real structure is going to settle 1 inch, 25 millimeters, Terzaghi's number is going to give you 1/10 of an inch, 2 or 3 millimeters, an order of magnitude. These are phony settlements you get from when you use Terzaghi's K values. In summary, and I have made the point, I think already, but I'll summarize it. He saw the beam on elastic foundation approach using constant coefficient of subgrade reaction, or K values, from the Fusswinkel hypothesis solely as an improvement to calculate local bending moments in a mat or slab on grade or rigid pavement. And certainly in the pre-computer era, Terzaghi's paper was genius. There's no doubt about it. But the need to do what Terzaghi proposed has not existed for decades. Again, coefficient subgrade reaction has never been a fundamental soil property. It's the unicorn of foundation engineering. It's a waste of time to go trying to relate it to soil properties. And Terzaghi himself pointed this out. It's a contrived parameter for a structural engineering goal, not a geotechnical goal. That's a function of soil type, flexural stiffness, and loading. And again, the decades of resources that have been spent trying to link this soil spring constant, if you will, to fundamental soil properties has been the biggest unicorn I've ever seen in 48 years of geotechnical engineering practice and teaching. Now, it appears for some years after Terzaghi's 1955 paper that foundation engineers really understood what Terzaghi was talking about. DeSimone and Gould, and I'm going to be looking at 2 of their case histories. And I knew both the late Sal DeSimone, who was a superb structural engineer, foundation engineer, and the late Jim Gould, who was a superb geotechnical engineer. They wrote a conference paper in 1972 that talked about 2 1960s era applications, right? So from the slide rule era. And if you ever want to see a case history paper written by 2 really outstanding practitioners who understood the limitation of Terzaghi's work, read this paper, please, because they nailed it. All right, they used this to calculate the local bending moments into actual mat foundations. Now, they chose to ignore the global bending moments because they were dealing with fine-grained soil conditions. They were concerned about immediate undrained loading versus long-term drain loading. And they also did a separate forecast of settlements just using a simple one-dimensional analysis based on odometer data. Now, it turns out their settlement forecasts were off, but it was simply a result of the lab data they had to work with in the early 1960s. But this is really the only paper I've ever seen of real-world foundation engineers who did this for a living, day in, day out, understanding the limitation of Terzaghis paper. Just about everything else I've seen since has been a misuse of Terzaghis work. So really, unfortunately, this very limited scope of Terzaghis work was rapidly forgotten. And I think this is part of the reason, a large part of the reason, why we're in this predicament we've been in for a very long time in foundation engineering with soil structure interaction analyses. Well, let's talk about state of practice in the present. What can we do realistically now and in the near future to make things better? I have no doubt in the longer term, the ideal analysis will be practical. Technology always grows. But what can we do now? What can we do now to make things better? We have no justification to use either the rigid method or Terzaghis approach. These were artifacts of the pre-computer era. I think it's a time, they were wonderful tools for their time. They should have been retired decades ago. People still cling on to them for a variety of reasons. There are two viable alternatives. I call them the structural approach and the geotechnical approach. The structural approach is by far superior, and the only one I'm going to explore in detail in the remainder of this presentation, but I will talk a little about the geotechnical approach for the sake of completeness. Whichever approach you use, I think at the present time it's realistic to assume that the analysis must yield one set of forecast settlements. This idea of, well, I've got these phony small settlements I use for structural design and these real settlements I use for geotechnical, there's no justification for that. Look, the real structure is going to have one set of settlements. Your analysis should produce one set of settlements, not two. And these should be realistic settlements, obviously. And again, as I've already said, we should not be basing structural designs on unrealistically small settlements. Now, what I call the structural approach combines the superstructure and mat into what we might call a megastructure for modeling and analysis purpose. This is very easily handled in commercially available structural analysis software and has been for decades now. We could do a really first-class state-of-art analysis of this combined system. The constraint of the structural approach is that you need to quantify the subgrade reaction. And again, I'm not implying it has to be a uniform applied stress here. This is just a cartoon for some subgrade reaction that could vary as a function of X and Y beneath the mat. Most importantly, you have to be able to model this subgrade reaction within the capability of structural analysis software. And again, this is structural engineering governing the problem, as I said earlier in this presentation. So we need to have a subgrade model to relate subgrade reaction to settlement, and this is where geotechnical engineers come in, but geotechnical engineers need to understand the constraints of structural software. And note in this approach, both of these subgrade reactions must be the same. We got to get away from this two different subgrade reactions, two different sets of settlement. Now the geotechnical approach combines the mat and the subgrade in one model. And here you tend to go to a geotechnical software package, typically finite element. I mean, you could do a state-of-the-art, build your three-dimensional bricks of the soil subgrade. You don't need a subgrade model. You could use a very exact constitutive model. But you need the input loads, Q of XY, and these would have to come from a separate structural analysis that is performed on the superstructure. And that's really the weak link here, is that you cannot analytically connect these two systems. The other weak link is that really you need to do two very complex separate analyses, and you might iterate to try to get these two applied loads to match, but it would be a tremendous amount of work by two separate structural and geotechnical engineering teams. So I'm not a fan of this approach. So for the rest of this presentation, I'm going to assume that the structural approach is technically superior, meaning that we geotechnical engineers have to come up with a subgrade model that works within the confines of structural analysis software. All right? So this is really the focus of the rest of this presentation. How can we come up with a good subgrade model to link subgrade reaction and settlement and stay within the confines of commercially available structural analysis software? And I think you'll see we could do pretty darn well nowadays. Well, now this brings us to the evolution of subgrade models. How do we craft a model that works within structural analysis software to give us the desired results? I've divided this segment into several topics, and I want to say at the outset that even for those of you who are familiar with using subgrade models, that I think a lot of the information I'm going to present is new to you. The things I'm going to present have appeared in the published literature, papers I've written. However, realistically, these papers have not gotten, I'm sure, widely read. Certainly, the information I'm going to present has not made it to textbooks, that much I can tell you. And as a result, I suspect that the vast majority of both practitioners as well as academicians are unfamiliar with a lot of what I'm going to present here. So I will probably emphasize things time and time again to hopefully make things clear. Well, some background thoughts. First of all, it's important to note that a subgrade model is never a complete constitutive model for subgrade materials and always involves significant approximations and compromises. That's because the goal of subgrade models, as I've touched on previously, always tries to strike a balance through some really competing factors. First of all, you're only looking to use that model for a relatively narrow, well-defined application. And that application typically has some behavioral features, and you're really looking to focus on that. I mean, for example, with mat foundations, you're looking at focusing what's the settlement of the mat. You know, what the lateral displacements of the subgrade are at some depth below the mat. You could care less for your very focused needs. Of course, we do have to consider theoretical rigor and implementation and practice and research. And again, I keep circling back to the fact that soil structure interaction analysis is, to a very significant extent, driven by what can we do within the confines of structural engineering and structural engineering software. And then we kind of work backward from that. This is a quote by Einstein. I'm sure it's appeared in countless places. In most cases, it's been distilled to the aphorism, make things as simple as possible, but no simpler. I suspect this has been seen a lot more than the original quote. However, I would like to recast this with regard to subgrade models is that we should make things as simple as necessary, but no simpler. Necessary being emphasized here. Because again, by necessary, I mean we are looking to capture certain behavioral features of the subgrade. There are certain things we need that are important. Is it lateral displacement? No. Is it vertical displacement? Yes. As we'll see, is it vertical shearing? Yes. So as simple as possible, simple as necessary, but no simple. Now, with regard to what some of these specific requirements are, as I said, total and differential settlements under service loads, displacements are important. If you have a mat foundation, it's settlements. If you have laterally loaded pile, it's lateral displacements at the head of the pile or along the pile shaft. So typically, the total and differential displacements in the direction normal to the interface between the structure and subgrade are of primary interest. As I've said previously, we need to reduce one of the dimensions of the problem by at least one. You have a 3D subgrade, it's got to be a 2D subgrade model. 2D subgrade, as in lateral load piles, a one-dimensional subgrade model is adequate. You must be able to relate the model parameters to fundamental soil properties and parameters. Although these model parameters are not in and of themselves fundamental soil properties, they have to be related to soil properties and problem parameters. You have to be able to solve it in the calculation tools available at the time. And it's really, this last point is where I think both practitioners and academicians, past and present, have failed. Calculation tools have changed drastically over the last century, 2 centuries. Things that were defensible in the pre-computer age are no longer defensible. But the bottom line is we should not be using 19th century models from Fuss and Winkler, in 20th century closed form solutions from Hatanyi that were solvable with a slide rule when we have these 21st century numerical tools available to us. It really not only makes no sense, it is not defensible. This is a quote from the editor of, this was a compilation volume. It's worth looking at. It was published about 20 years ago dealing with mat or raft foundations. And this basically states in another way what I've just said. Yes, in the past we did things a certain way. We used the conventional method of static equilibrium, rigid method. We used beam on elastic foundation and Terzaghi's coefficient of subgrade reaction values because we didn't have any alternatives. And yes, certainly if we look at some of the case histories I'll show you later that were designed on this basis, they have performed satisfactorily for the last almost 60 years. But that doesn't mean we need to do that today. I remember in my education, a structural engineering professor telling me that, they were able to design and build the Empire State Building in New York City, which was certainly a hallmark tall building for its day. They were able to design and build that in a pre-computer era. Now, if you were to replicate that building today, would you analyze it with the same 1930s era analytical tools? I rather doubt it. In fact, if you did, you could probably be successfully sued for professional negligence for doing that. So, just because we did things in the past and they worked out okay, it doesn't mean we have to do them the same way in the future if we have better tools available to us. Kind of an overview of this segment. Again, I'm going to be focusing on a mat or raft foundation supporting a building of some type using the so-called structural approach. This is where We use structural analysis software to accurately model the superstructure and mat combined into a megastructure. And we need to have some subgrade model that we input into that. The subgrade model has to be doable within the confines or the limitations of the structural engineering software. And we need to take into account that the capabilities of the structural software have improved with time. So the models that we can use have advanced as well, although there seems to be a curious lag in doing so. Basically what I'm trying to say here is, why have we as geotechnical engineers developing subgrade models, why have we not kept up with the capabilities of structural analysis software? It can do all these things I talked about, linear analysis, shear effects, right? Why have we not made use of that? Now, when you're talking about the evolution of some technology, whether it was slope stability analysis or lateral earth pressures or settlements of a footing, very frequently the tool that is used by whomever is writing a paper or research report, whatever, is to use what I call a timeline approach. So you present in a monotonic progressing manner how this technology changed over time. And that's usually pretty successful, because most technologies tend to build on themselves as time progresses. Now, I've been dealing with subgrade modeling and models going back to the 1970s when I did my doctoral research, and I found that this temporal approach to things, to a presentation, does not work well in this case. And that's really because in the case of subgrade models, the body of knowledge has really appeared in very widely scattered venues. They've appeared in papers and in research reports in the applied sciences that civil engineers don't read, for example. So it's really been a technology transfer problem. Material related to subgrade models has appeared in a very wide variety of venues, and realistically, no one person can, in real time, read all of these things. And I will tell you, from having gone through my doctoral research in the 1970s, that the way that I turned up a lot of this material is you would find a paper. And one of the first things I did is I would look at the references and then go read every single reference to that paper, which certainly in the days before the internet was a challenge, because you had to get copies of things from libraries or whatever. So yes, it is certainly possible to dig out all of this information from a variety of sources, but it is not something that it took me 6 years to do. Not something that the everyday practitioner or even academician is going to do in a short period of time. So my point is, there's a lot of work that's appeared, especially in the applied mechanics and mathematical literature, that foundation engineers don't know about, even though it was published almost 100 years ago, 80 years ago. So as a result, I think this is a good part of the reason why foundation engineers tend to cling to things that we really should have abandoned a very, very long. I now see things that there's really a common unifying, what I call theoretical umbrella, that is the best way to present and to visualize subgrade models. I don't use time as the unifying concept. I build it around what I call Poisson's solution. Poisson in 1939, so over 80 years ago, published a theory of elasticity solution, and he considered a perfectly linear elastic layer, finite thickness on a rigid base. And what was interesting is the way he presented the solution was as infinite series. So it was an infinite series involving the subgrade reaction P and multiple derivatives of P. And again, this second derivative, fourth derivative, I'm using this shorthand. And an infinite series of settlement. So it was a rather interesting way to portray the solution. And I think this is really the unifying concept that I use. This is an exact solution. These two infinite series equated to each other. It's an infinite solution to a theory of elasticity problem that reasonably approximates a subgrade of finite thickness resting on a rigid base. Now, in reality, an actual subgrade model will only have a finite number of terms on either side. So as we're going to see, the way to basically categorize or rank subgrade models is by how many terms on each side of the equation they use. Now, in general, I think you would agree that as with any infinite series, the more terms you retain, the more accurate the answer or solution. And this is true, but there are going to be some exceptions. We're going to see that there have been some subgrade models that people have dreamed up that unfortunately skip over intermediate terms. So it's unclear whether they're really better or not. The challenge of using Poisson's solution is you've got to evaluate these constant coefficients. So first of all, you need to visualize them in some physical manner, because as he presented them, they were just unknown coefficients. So that's really the first step. You got to come up with a physical model, because it's really, you need to visualize something to be able to model it in structural analysis software. Now, as it turns out, there have been two very distinctly different approaches that have evolved over the last 200 years. Most of this evolution was in the middle decades of the 20th century, 1940s, 50s, 60s, that sort of time frame. The first is what I call the mechanical approach, and this is really the older of the two, that uses assemblages of what I call mechanical elements. And these are independent axial springs, tension membranes, shear-only layers, and flexure-only layers, stacked one above the other. And then there is what I call the simplified continuum approach. And this is, we start with the sets of partial differential equations, constitutive, equilibrium, compatibility, that define the behavior of any elastic continuum, and then we make some judicious simplifying assumptions. As you can see, these two approaches have absolutely nothing to do with each other, completely independent. Most of this work appeared in the applied mechanics or engineering mechanics literature, so it was kind of out of sight to the everyday foundation engineers, even academicians who were involved primarily with foundation engineering. So that's really why it's kind of stayed hidden for so long. It really was not published in venues that the normal civil engineer, for example, would access. So these two approaches have nothing in common, but as we could see, we can actually use the Poisson solution to link these two together. And that's really the key element of this segment of the presentation. Because you can develop a subgrade model of equivalent mathematical order, which we assume relates to accuracy using either approach. No surprise, there's pros and cons to each approach. And out of this has come what I call the hybrid or composite approach to things. So we, as the colloquial expression goes, we cherry pick. We take the best of both worlds, the best of the mechanical approach, the best of the simplified continuum approach. We combine them into what I call the hybrid approach. And this really gives this hybrid models, gives us something that are pretty good, I think, and most importantly, usable in current practice worldwide in structural analysis software that any structural engineer can access. Now, there's always room for improvement. I mean, after all, Poisson solution is an infinite series. So it tells us, no, not to make a joke about it, but it does tell us that there are limitless opportunities to improve on what we do. So I don't want you to think that the work I'm presenting here is the final story. There's certainly room for people to come up with even more advanced models. And as long as they can be implemented in structural analysis software, they're probably better to use than anything I'm going to show you here. Well, let's first start talking about mechanical models, which are certainly older. As I said, depending on whom you want to believe, they originated in the 19th century with either Winkler or Nicholas or Nikolai Fuss. Fuss was a Swiss mathematician, spent much of his professional life in Russia, Imperial Russia, hence the dual versions of his given name. But what I call the Fuss-Winkler hypothesis is just an abstract mathematical statement. Subgrade reaction is related to subgrade settlement by this coefficient. Now we can relate this to the Poisson solution by noting that here we see that the Fuss-Winkler hypothesis is now recognized as the simplest subgrade model we can come up with because we retain the first terms on either side of Poisson's infinite series. And we see the correlation between, okay, now we know that this CW1 coefficient is really the coefficient of subgrade reaction. I'm using a different notation here for the coefficient of subgrade reaction because I don't want to confuse it with a generic coefficient that is really a problem output calculated result. This has to be a known input parameter. Now, one thing I do want to emphasize is in the Fuss-Winkler hypothesis, this does not have to be a constant. That was really Terzagh's assumption that this K value is constant, and that was so he could use the beam on elastic foundation solution. Most of Hitani's solutions assumed a constant coefficient of subgrade reaction. That was just a pragmatic necessity. Unfortunately, I think there's a lot of foundation engineers have gotten into the habit or assumption that somehow this has to be a constant. It certainly does not. Now, it was only later that someone, and I've never been able to find out whom, interpreted this to be either an independent layer of axial springs of stiffness force per length per unit area, where this is essentially the spring constant, or a liquid with a unit weight. And by the way, not density. Okay, density and unit weight are not the same things. I know that even a lot of civil engineers who should know better use these terms synonymously. They are not the same. Unit weight is a weight or force per unit volume. Density is a mass per unit volume. Curiously, and this is just an aside, I've seen in many publications people say, oh, a dense liquid. I don't know why they need to use the adjective dense here. It's a liquid. I mean, I don't know whether they think it's somehow got to be dense so this mat will float on it. From that perspective, I guess that's where they're coming from. But it's just got to be liquid. There's no need to say dense. I'm only going to use the spring analogy. It's far more common and enduring in practice. It also kind of is visually pleasing for the way that a real soil subgrade behaves. Now, we've known for a very long time that the Fuss-Winkler hypothesis with a constant coefficient of subgrade action was fatally deficient. If we compare it to real-world behavior, I mean, for example, if you apply a uniform stress to a foundation element, the Fuss-Winkler subgrade says you get uniform settlement. Well, you don't get that. It says you only get settlement within the loaded area. Well, you get settlement outside the loaded area. Although it's not shown here, it says you get a uniform bearing stress or subgrade reaction. Well, you don't get that. So we've known for a long time, this is not new, that a constant coefficient of subgrade reaction is simply incorrect. Has it stopped people from assuming that? Absolutely not. It's just been dead wrong, and we've known that for a very long time. Really, what's missing from the Fusswinkel hypothesis is most people refer to as what's called spring coupling. And this is because a convenient way using the spring analogy is to assume that in the real world, these springs are actually linked together. Push on one spring, well, you're going to affect the springs on either side of it, which will affect the springs on either side of that spring. So you're going to get some load spreading. You're going to get some lateral distribution of vertical loads via this vertical shearing that is inherent within a real subgrade, whether it's soil or any other type of geomaterial. Well, there's two approaches to dealing with this lack of spring coupling. One is what I call true coupling, and this is the development of multi-parameter mechanical subgrade models that inherently incorporate spring coupling in the mathematics of the model. And then there's what I call the pseudo-coupled concept, where people stick with the uncoupled springs of the Fuss-Winkler subgrade, but then come up with all sorts of strategies and gimmicks and guesses to try to guess how these springs vary. And we'll talk about both of these in separate sections of this segment. Well, let's start off with true coupling. I mean, this is really the better way to go about it. Now, all multi-parameter mechanical subgrade models that have inherent or true spring coupling build on the Fuss-Winkler subgrade. And they add additional mechanical elements, either a tension membrane, a shear-only layer, a flexure-only plate. You can add an additional spring layer, but there's got to be something between that and the lower spring layer. All these elements extend by default to infinity in the XY directions, but as I'll show you later, you can actually develop special boundary conditions or edge elements so that you can truncate the mechanical elements. The way these mechanical elements behave is not unique. For example, a tension membrane and a shear layer produce the same behavior. And by shear layer, I mean a layer that behaves only with shear, no flexure. In the same way, this flexure-only plate only has bending, no shear effects. Also, a shear layer or tension membrane over layer springs produce the same as a plate. I point this out because when you're playing around with building subgrade models, as I have over the last several decades, you find that there are certain mechanical elements that are easier to program in structural analysis software. For example, a tension membrane is much easier to program than a shear-only layer. So, you know, it's useful to use some of these redundancies to kind of tinker with the model that you input. I'm not going to go through a quick summary of these multi-parameter models. I certainly talk about them in much greater detail in other publications that I've had over the years. So this is just a quick overview. I'll start with, although the Fuss-Winkler hypothesis is obviously not a multi-parameter model, I start by showing it just to have kind of a common viewpoint to see how I build on these other models. And again, we see this is the simplest subgrade model we could have. The oldest multi-parameter model I ever found was the Filanenko-Borodich model. Placed a tension membrane over the spring layer. This was the additional term that the tension membrane introduced, and you see it added another term to the settlement side of the infinite series. So this type of equation, pressure is equal to settlement plus the second derivative settlement. This is the simplest multi-parameter or advanced model that inherently has spring coupling. And in this case, it's really the tension membrane that is providing the coupling between the springs. You're tying all these springs together by this membrane. It has to be under an initial tension. That's an important assumption. And we see now, again, using this correlation, this now, again, this is this parameter, this is this parameter. As you'll see, I've color-coded these things just to make this visual linkage easier to see. We then have a hypothesis, Pasternak in the 1950s, and then a separate researcher some years later named Loof came up with the same hypothesis. They just assumed a mathematical expression. It was Arnold Kerr, the late Professor Arnold Kerr from New York University and University of Delaware, who visualized this as a shear-only layer. And actually, you get the same differential equation as the Filanenko-Bordich model with the tension membrane, because as I said, a shear-only layer. And I use a lowercase g. This is not the shear modulus. This is just a shear constant in this case for this fictitious layer. You get the same differential equation as the tension membrane. Right? And again, this is how the parameters correlate. Arnold Kerr went a step further. He put another spring layer on top of the shear-only layer. Call this the Kerr or modified Pasternak model. And we see that this adds now a term to the pressure side. Right? This adds second derivative of pressure. So notice how we're methodically building on, we're fleshing out the parameters in Poisson's infinite series as we're building ever more accurate subgrade models. And again, here you see the correlation between coefficients. This is really essential. Some years ago, I collaborated with Horvath-Colasanti, whose name I'll mention more as we go into things. We modified the Kerr model by substituting a tension membrane for the shear layer. And this actually was to give a model that was much more easily implemented in structural analysis software. We also developed a boundary condition for this model that other researchers in general have not developed a boundary condition. Again, it's important to keep in mind these models go on to infinity horizontally in both the x and y directions. And it would be nice, certainly, when you put this into a structural program, to be able to truncate the model at the edge of the foundation. You don't want to be modeling this to infinity, obviously. So very few researchers have come up with the appropriate boundary conditions. Regis and I certainly did this. Again, you see relative to the Poisson solution. Habersham wrote a little monograph some decades ago, and I call this the modified Hertz model because Hertz actually came up with a subgrade model that was a flexure-only plate over a liquid. Habersham came along some years later and instead of visualizing this as a liquid, used a spring analogy. But this is just a structural plate, bending-only plate over a spring layer. And this is the resulting differential equation. Now, the interesting thing with this is a case where notice that it jumps over an intermediate term, right? This model jumps over the second derivative term, goes right from no derivative to the fourth derivative. Is this more accurate than a model with the second derivative? It's not clear-cut that it is. And again, we see the correlation between Hatanyi, who's in his monograph, 1946 monograph on beam unelastic foundation, he did also come up with his own subgrade model, and he put springs over a structural plate. This is the resulting differential equation. You see that this adds a fourth derivative on either side, but notice that his model jumps over two terms, one on each side. Again, begs the question, is this really more advanced than something that includes these terms? We now come to what I call the Reissner model, which is the most advanced mechanical subgrade model I've ever seen in the published literature. And this is what I call the kitchen sink. All right, Reissner's put just about one of everything: spring layer, flexure only plate, shear only layer on top of a bed of springs. Point out that this shear layer could be replaced by a tension membrane. And this was the resulting differential equation. As you can see, added two terms on each side to the original Fuss-Winkler hypothesis. So this is the most advanced subgrade model I've ever seen to date. It has three terms on either side of the Poisson solution. And you see the correlation between parameters here. Now, in the 1960s, Reissner, who was Professor Arnold Kerr's doctoral student at the original New York University Engineering School, it was the one that was located in the Bronx, New York City, wrote a nice little research report that showed that this process of mechanical subgrade model building, if you will, can go on as long as you want. You just keep adding mechanical layers of mechanical elements. They showed it up to a 10-order equation. As you can see, at some point it becomes non-unique, obviously. As I pointed out previously, you could replace a flexural plate by a shear layer and a spring layer. And of course, in the limit, an infinite number of mechanical layers would be the theoretically exact solution, or Poisson solution. So a useful way to visualize this building block concept in mechanical subgrade models is to categorize and rank these models in terms of the order of derivatives of the primary problem variables, subgrade reaction and settlement. And I've done this in this table here. We see the order of the derivatives, 0, 2, and 4, and each of the models. So we can categorize mechanical model, subgrade models, as we might call bottom-up model building. We start with the simplest, the Fuss-Winkler hypothesis, just a layer of independent springs, and we keep on adding elements for as long as we like. And we see that the higher you go with the more terms, the more accurate the model. Although one does have to question the Habersheim and Hitani models, which neglected intermediate elements. So it's kind of hard to see, you know, is the Habersheim model, for example, inherently better than the Kerr model or the Horvath-Colasanti model? It's not clear. But these are the models that have inherent spring coupling, right? It's built into the mathematics of the model. There's no guesswork involved. Well, we want to compare that to pseudo-coupled models. As I said, the pseudo-coupling concept is an alternative way to deal with this inherent lack of spring coupling, as we call it, for the Fuss-Winkler subgrade. It's been, in my experience, difficult to get both practitioners and researchers to embrace multi-parameter subgrade models. And this is something I've thought about quite a bit over the last 40 plus years that I've been researching this topic. I think there's a certain mental inertia of the Fuss-Winkler hypothesis, which goes back something like 200 years now, as well as what I call the Terzaghi effect. And I don't mean this to certainly, in the least, deprecate Terzaghis work, but I think there's a certain tendency when you have someone who was so important to the field of geotechnical engineering, such as Terzaghi and some of these other early pioneers like Peck, that if they came up with something, it's hard for people to say, well, yeah, that was right at one time, but there's something better. This is what I call the Terzaghi effect. If Terzaghi came up with it, it's got to be the best way to do it. Well, in all fairness to Terzaghi, he may not agree with that. You know, it may have been the best in the 1920s or 1930s or 1955 when Terzaghi wrote his geotechnique paper without digital computers and only a slide rule, but is it the best now in year 2020? I kind of doubt it. A large part of it is that people have forgotten Terzaghi's very narrow, limited use of the Fusswinkler subgrade as a structural analysis tool. I mean, Terzaghi himself said it. Don't use it for settlements. I don't know what could be more clear than that. One of the benefits, I guess, of the Fusswinkler hypothesis, you don't have to worry about edge boundary conditions. With uncoupled springs, where there's no load, the springs don't deflect. So there are no boundary conditions you have to worry about. And you can see that for the fundamental differential equations, that using the Fusswinkler hypothesis, where we replace subgrade reaction by the coefficient of subgrade reaction and settlement, no matter whose equation you want to include, or with the stiffness matrix concept, it's very easy to implement in practice. We can really see this with the stiffness matrix, where we see that we can replace the vector of subgrade reactions with a separate stiffness matrix of the coefficient of subgrade reaction and displacements. And by some algebraic manipulation, we come up with a final result that shows we can have an expanded enhanced stiffness matrix, where basically all of the subgrade effects are folded into the original stiffness matrix. And if K is constant, well, it makes it even easier. And in the process, obviously, we've gotten rid of the subgrade reaction as a separate problem parameter and variable. So the point I'm getting at here is that I think one of the reasons why people continue to want to try to work with the Fusswinkler hypothesis, even though we've known for decades, it's a terrible model. It doesn't include spring coupling or the vertical shear effects of real subgrades, but it's just so easy to use in structural analysis software. It's very seductive from that perspective to continue to use it. Because you've eliminated subgrade reaction as a problem parameter. You folded everything into being a function. And the so-called pseudo-couple concept has evolved to make use of this. It's built around the thought that the real subgrade reaction is not uniform, so this should not be constant. The coefficient of subgrade reaction needs to be non-uniform, but how? Well, there's a number of strategies come up. The simplest one simply said, well, double the K value at the edges of the map. I'm not even going to comment on the logic of doing that. Some people have tried to approximate this curve relationship using a theory of elasticity solution. What I call Lau's method is usable or is interesting for a very project-specific application. And in this case, what you do is you do a rigorous finite element analysis of the real problem. Now, in Lau's case, these were cut and cover tunnels. So you do a rigorous analysis you see how the spring constant, if you will, varies, and then you use that in other analyses. Now, in Lau's case, this was used on the Boston Big Dig Highway project some 20 plus years ago, where they were building many cut and cover tunnels. They had the same basic geometry, so they came up with a way of estimating how the springs, if you will, beneath the tunnel would vary, and just replicated that for different sections of the tunnel. So it's one of the rare cases where you can reasonably satisfy this otherwise absurd requirement that you need to know the correct answer beforehand so that you can put in the correct values of, in this case, the spring values to produce the correct answer. Another kind of clever approach is Ulrich's discrete area method, where you take a mat foundation, you divide it into arbitrary checkerboard of discrete areas. So for each of these discrete areas, and they don't have to be the same size or shape, but you assume that each one has a different value of the spring constant, and thus the subgrade reaction can vary from one little discrete area to another. So what you do is you have two simultaneous analyses. You have the structural engineer does an analysis of the megastructure, the superstructure, and mat using structural software. And at the same time, the geotechnical engineer uses some geotechnical program. Now, it could be finite element program, it could be a layer elastic program. And each of them uses the same checkerboard in their separate structure analytical models. And they each vary the subgrade reactions and the spring values until the results of their analyses match, the settlements match, and or at least match within their satisfaction. And that's obviously quite subjective. Now, this is a method it's been around for some decades, and again, it's been used on several projects. But it's really, in my opinion, it's very cumbersome. It requires a structural engineer and a geotechnical engineer who have worked together before. You know, they can each understand what they're doing and come up with solutions to the two separate analyses that produce an acceptable match. But is this a general purpose method? No, not in the least, in my opinion. No matter how you slice it, no matter what the strategy is employed, you have to understand that the pseudo-coupled concept means that through some strategy, whether it's guesswork or analytical, it is the burden is on the design professional to estimate what the spring coupling or vertical shear effects in the real soil subgrade are beforehand. So again, it's the price you pay for using such a simple mechanical model such as the Fuss-Winkler subgrade that does not have any inherent shear coupling or shear interaction. The burden is on the analyst to think up this spring coupling beforehand, put it into the program, and then calculate the right answer. So we can't get away from it. With pseudo coupling, you're still coming down to the fact that somehow you need to know or estimate the correct answer beforehand so you can input it into the correct input to calculate the correct answer. The bottom line is I am not obviously a fan of the pseudo-coupled concept. Obviously there are some people who are and have promoted it very aggressively in recent decades, but it is not a general purpose approach to the problem. Really, the approach to the problem is to use a multi-parameter subgrade model that inherently incorporates spring coupling. Well, I now want to talk about simplified continuum models, and I suspect that these models are quite unfamiliar to most foundation engineers because other than papers I've written on the subject, most of the publications involving simplified continuum models have appeared in the applied mechanics literature. Simplified continuum models really trace their origins to Eric Reissner in the middle of the 20th century. And Reissner assumed an elastic layer of finite thickness, h, over a rigid base. And he made a number of simplifying assumptions. He neglected compatibility equations. He simplified the constitutive or stress-strain equations. He did satisfy force equilibrium. And I want to point out that in the simplified continuum concept for subgrade models, the vertical shear stress within this elastic layer is the equivalent of spring coupling in mechanical subgrade model. So that really is the key element. You remember earlier I said that when you're developing a subgrade model, you need to focus on what are the key parameters in that particular application. Well, obviously settlement is the primary one, but if we want to have inherent spring coupling in a subgrade model, we need to include vertical shear stress. That's a parameter that we need to retain in the simplification process. The simplified continuum concept was really the heart of my doctoral research and dissertation in the 1970s. I started with Reissner's original solution. I did change the coordinate axes to be more geotechnical in nature. He only solved for a Young's modulus that was constant with depth. I developed a solution for Young's modulus that varied linearly with depth, allowing for an initial value, as well as one that varied at the square root of depth, allowing for initial value. I also allowed for a overlying elastic plate, which obviously simulates a mat foundation. And I analyzed two boundary conditions, one that was perfectly frictionless and one that was perfectly adherent between the two. And I also extended the simplified continuum concept to the Pasternak and Fusswinkler type of subgrades. First, look at the Reissner's original Young's modulus constant with depth with a perfectly smooth interface between a foundation element and elastic layer. This is the resulting differential equation, which again, if we compare this to the Poisson solution, we see that essentially this is the same as retaining or having two parameters on each side of the equation. So we see that we do have inherent spring coupling, if you will, built into this simplified continuum by virtue of these higher order parameters. As I said, I extended this to a perfectly rough interface between the plate and elastic layer, and we get a slightly different differential equation that includes the thickness T of the plate. It does make a small change of things. It's not only on this one parameter. And as I said, I also developed exact solutions for E that was varying linearly of the square root of depth. They have only been published in my doctoral dissertation. They're very, very lengthy algebraic expressions. See, these are fairly simple expressions for these coefficients, CP1, CW1, CW2. The coefficients are much, much more complex algebraically. It's just algebra for these other two cases. As I said, one can keep on getting simpler from Reissner's case. If you make some additional assumptions, you could wind up in the equation has the same form as the Pasternak-Loof hypothesis. And keep on going, you can actually wind up with a simplified elastic equation that is the same as the Fusswinkler hypothesis. And this is really interesting because if you think about it for the first time, what the simplified continuum concept provides is really fundamental insight is what's the implication of the Fusswinkler hypothesis, that is, springs without any coupling, and the meaning of this mythical coefficient of subgrade reaction that we've been chasing after for decades. And we see it's basically means it's the same as an elastic subgrade that has no vertical shearing, where the vertical stiffness is just the Young's modulus divided by the thickness of the layer with no vertical shearing going on. And again, vertical shearing in a simplified continuum model is equivalent to the spring coupling in a mechanical model. Well, we could do the same categorization in a tabular form as I showed you previously for mechanical models. But we see that with the simplified continuum concept, it's a top-down model building process. All right, you remember with mechanical models, we started simple and got more complex. Well, with a simplified continuum, you start complex, and then you keep on simplifying or dumbing down, if you will, the partial differential equations to get a subgrade model. Now, it is true that to date at least, mechanical subgrade models have been explored to a higher level. You recall that Rhine's model had 3 terms on either side of the equation. The most complex subgrade simplified continuum model to date has been Reissner's model with 2 terms, but certainly there's no reason that one could not develop more complex simplified continuum models. You just have to make fewer simplifying assumptions than Reissner or I made. I do want to point out that there have been other researchers, such as Vlasov and Leontov, who have approached the simplified continuum concept from a little bit different perspective. They made different assumptions, and they've wound up with comparable models. The problem with the Vlasov-Leontov approach is that they inject a unique parameter into their assumptions that, in my opinion, is pretty difficult to quantify in a real-world application. It's just an abstract parameter. So with Vlasov and Leontov, you basically get the same thing as using Reissner's approach, but with an additional complication. So there's really no benefit that I see. But the point still remains that there have been a number of people who have looked at this concept of let's build a subgrade model by making approximations or simplifications to a elastic continuum. Well, we now move on to the final topic of this segment of the evolution of subgrade models, talking about hybrid, or if you will, composite models. And this is the segment that I think will be new to the vast majority of people who are viewing this presentation. It's no surprise that both mechanical and simplified continuum models have pros and cons. With mechanical models, certainly we can visualize what these mechanical elements are. It's pretty unambiguous what a spring is, and pretty straightforward to model that in structural analysis software. But how do you come up with spring constants, or what's the tension in a tension membrane, or the shear in a shear layer? That's not the shear modulus, but what is it? It's really difficult to rationally quantify these abstract mechanical elements. And you need to do that, right? You've got to put numbers into your structural program. On the other hand, with the simplified continuum models, modeling a simplified elastic layer in commercial software, that's not exactly straightforward. However, quantifying the equation coefficients is pretty straightforward. It involves Young's modulus, shear modulus, the problem geometry. So, these advanced multi-parameter subgrade models, both mechanical and simplified continuum, they've been around a long time. I mean, Filanenko-Borodich proposed his model back in 1940. I mean, Reissner published his work in the 1950s. So these have been around a very long time. Why haven't they been embraced by foundation engineer practitioners and researchers? And the simple reason is that there are some problems with both mechanical and simplified continuum models as they exist in and of themselves. I mean, I published my dissertation 40 years ago, and realistically, it has not been embraced in practice. And I think this inability to use mechanical or simplified continuum models in their true sense really has led to contributed to the continued misuse of Terzagh's approach to things, as well as people looking at these gimmicks and workarounds such as the pseudo-couple concept. Well, it occurred to me in the last number of years that one way to overcome the negatives is to develop these hybrid subgrade models, which make use of mechanical and simplified models, but use the best of each one. And it's based on the concept that whether you have mechanical models or simplified continuum models, you're going to wind up with differential equations of the same order of derivative. Right. So we've looked at these individually. Now we put them together into a single table or matrix. And if we judiciously pick models of the same type, and I'm choosing models here that have a tension membrane instead of a shear-only layer because it's easier to program in structural software, we wind up with these hybrid models. And what the hybrid model is that we use the mechanical elements of the mechanical model because we can readily visualize and model these in commercially available structural analysis software. But then we define these abstract K's and T's and things like that in terms of the coefficients of the simplified continuum models. Now, I've done this hybridization process to date for 3 models, 2 of which inherently include vertical shearing / spring coupling in their formulation. And the most advanced of these hybrid models I call the Horvath-Colasanti Reissner model, where it combines the mechanical model that I developed with Reissner-Colasanti along with a Reissner simplified continuum. And again, the reason that Reissner-Colasanti and I developed our mechanical models is we found that a tension membrane was far easier to program into commercial software than a shear-only layer, such as in the Kerr model. So what are the basics of this hybrid subgrade model? Well, the physical model that you put into commercially available structural analysis software is pretty straightforward. You've got 2 spring layers, we call them upper and lower spring layers, and you've got a tension membrane. And then we quantify these abstract spring stiffnesses and tension in the mechanical model by correlating them with the coefficients in the Reissner simplified continuum. Now here I'm showing Reissner simplified continuum in its generic form using CP1, CW1, CW2. And I'll show you why in a second. And that's because these coefficients will vary depending on which particular solution case we have. E that is constant with depth, varying linearly with depth or with the square root of depth, and whether we have a perfectly smooth or perfectly rough interface between say, the mat foundation and the subgrade. So how exactly we populate these three parameters here will depend on the particular solution we're using. So the results of this process are, we see how we can quantify the spring layers and the tension membrane in terms of these parameters that come from the Reissner simplified continuum. Now, to illustrate this for one particular case, let's look at the most basic case, that of an elastic layer with a constant Young's modulus and an assumed perfectly smooth interface between, say, a mat foundation and the subgrade. And this is the case originally solved by Reissner. So in this case, this is CP1, this is CW1, this is CW2. These are very simple algebraically. As I said, if we now go to linearly variation or square root of variation with depth, these become literally pages of algebra. These are quite complex algebraically. If you're interested, you can find it in my doctoral dissertation. It's the only place those have been published to date. And we can then solve this. All right, so for this most basic case, which actually turns out to be pretty usable in practice, this is how you would quantify the spring to stiffnesses and this fictitious tension membrane in terms of the elastic parameters and physical thickness of this subgrade. So this is the heart of what I call the hybrid subgrade model process. You program in mechanical elements into structural analysis software, very straightforward, very easy to do, but then you quantify these in terms of geotechnical parameters of the subgrade in question. And I will illustrate this for some case histories later on. Well, before we get to the case histories, we need to have some additional comments with how we apply hybrid models to mat foundations. Obviously, I believe that at the present time we should only be using these hybrid subgrade models in both practice and research. So the point is of this particular segment is there are some additional considerations to make before we can look at some mat foundation case histories. Now, and that's because in the preceding presentation, although I used a mat foundation for illustration purposes, the subgrade models I've shown you, whether they're mechanical or simplified continuum or hybrid, can really be used in a wide range of soil structure interaction applications, where the structural element is horizontal, like a mat, or it could be vertical, like a flexible wall. In recent years, there have been people who have used subgrade models to include planar geosynthetics, like a geograde or geotextile, where the subgrade model represents the behavior of not just the soil, but actually as the geosynthetic embedded within it as well. So the point I'm getting at is, although I used a mat foundation to illustrate subgrade models, these subgrade models can be used in a very wide variety of problems. Like I indicated earlier on in that Army Corps of Engineers publication from the 1990s, they showed how to use the beam column solution for a beam on a subgrade, for laterally loaded pile, and for a anchored bulkhead. So depending on the specific application, you have to do a little bit more work to make these hybrid subgrade models usable. And again, I'm going to show how to do this for a mat foundation. So one of the things you have to look at to basically fine-tune these subgrade models for a particular application, well, you have to consider boundary conditions. Again, you got to remember that these multi-parameter models, they go on to infinity. in horizontal or vertical directions, depending on the orientation. And you want to be able to truncate them at the edge of the structural element, just for computational sake. You need to be able to assess the model parameters, obviously, and you need to implement them in structural software, unless, for example, you're developing some application-specific software. And for example, they've done this with laterally loaded deep foundations. I mean, there are commercial software packages that just use PY curves to solve laterally loaded deep foundations. But if you want to use this in more general structural analysis software, you have to do a little bit more work. Well, with regard to boundary conditions, you want to be able to end the subgrade model at the edge of the foundation element. And this is just a pragmatic requirement. And this comes about, again, because unlike with a Fuss-Winkler subgrade, where the springs are not connected, with a multi-parameter model, you are going to get settlement even where there is no load applied to the subgrade. So again, we're using the Horvath-Colasanti mechanical subgrade model, which is what we're going to want to use in our structural analysis program. The mat ends here, but the subgrade theoretically goes on forever. We'd like to be able to truncate this. So this is the actual model. Of course, we realize that in reality, these upper springs are not loaded because there is no load out here. So we need to come up with a equivalent for this tension membrane and springs that go to infinity. And I'm not going to show the derivation here. It appears in this reference and others, that you can come up with a special edge spring, defined as shown here, based on tension membrane and lower spring. So basically, in your structural model, you put, in addition to the tension at the edge, you put the special spring that basically includes all of these effects. So depending on your specific application, you would have to develop your own boundary conditions. No big deal. In terms of model parameter assessment, again, using mat foundations as an example, you would have your site characterization program, and you would define a stratigraphy of some sort, and you would define the elastic parameters for these different layers in your stratigraphy. This is a geotechnical problem. It's very straightforward. You would then develop an idealized layered elastic system where you'd have some arbitrary number of artificial layers where each layer had different elastic parameters. And then you would have to come up with an equivalent single layer elastic system. And that would have two components. It would have an artificial depth h to an effective rigid base, and it would have single valued elastic parameters. And I'll give you some guidance as to how to do this. And then once you have these parameters, it then becomes easy to calculate your spring stiffnesses, tension that gets input into your structural analysis software. So the geotechnical engineer, she or he, has to do some work to come up with this part of the problem, to quantify these parameters that the structural engineer then puts into his or her program to solve the problem. So the goal is to come up with operative values of the elastic parameters for this equivalent single layer elastic system of artificial thickness H. Now, I found, after using this for a couple of decades now, that really the determination of H is the most critical issue here. And certainly for a mat foundation problem, it would be the smaller value of the distance to a real physical rigid base, quote unquote. This would be, say, rock beneath soil, or perhaps coarse grained soil beneath fine grained soil, or the depth to an effective rigid base where the settlement caused by the structure applied load is effectively zero. And I found that in most cases, this is what governs. There's no one best way to do this, as to some extent it does depend on the stiffness of the soil, which means some sort of iterative trial and error process is required. But obviously it's doable, or I wouldn't be talking about this here today. I'll share with you some broad trends that have been observed with actual structures, as well as from research. First and foremost, you never want to use that one-size-fits-all rule of thumb of the effective depth is twice the width of a footing for a square. It's much too large. It simply should never be used. It came about from using Boussinesq solution and only looking at the stress increase, not looking at the overall problem. And that's because research has shown two things: that this H over B ratio decreases in magnitude as a result of two things. First of all, as B gets larger. And this is a plot that Berlin and Burbidge published in a geotechnique paper in 1985 of some observed results. And they also came up with an empirical equation that approximates these results, and I've just calculated values of this empirical equation for multiples of 10. And notice this is a log scale up here. This is an arithmetic scale. So, and this is sensitive to units. This is only for meters. So again, this would be about 3 feet, 30 feet, 300 feet in imperial units. But notice quite a bit less than the 2 rule of thumb that has been around for a long time based on kind of a misinterpretation of sorts of the Boussinesq solution. And this is because when you use the Boussinesq solution that says 2b, that only comes from where the stress increase decreases to a small value. But you really need to look at the stress increase relative to the pre-existing vertical effective stress. What we're saying here is at some point as you get in the ground, the stress increase is negligible relative to the overburden stresses that exist there. Believe me, I've spent a lifetime of trying to explain to non-engineering friends and relatives why Manhattan Island does not sink under the weight of all the high-rise buildings built there. Spent a lot of time trying to explain, well, you see, if you go deep enough, yeah, the building weighs a lot, but the ground doesn't feel it. And at that point, they turn around and go somewhere else to talk to somebody else. Anyway, this is a nice little paper that Charles published in Geotechnique in 1996 called the MT method. Now, he was interested in large earthworks on the surface of relatively soft subgrades to show this significant stress depth, if you will. I found that it can be generalized and used for large foundation elements such as mats as an alternative to the Berlin to Burbidge empirical relationship for coarse grained soils. And I've used this, I call this the MTH method. I talk about it in this reference here that I'll give you at the end. And also in this MTH method, I've used it to come up with an estimate of the single valued Young's modulus and shear modulus in addition to this fictitious value of a rigid base H. So the point I'm getting at, I think there are some pretty sound, reasonable ways to estimate this, and I will show you how I've done this for 4 case histories. And I think the results have come out to be pretty reasonable. There are other strain-weighted methodologies. Fraser and Wardle talked about this back in the 70s. Again, another geotechnique paper for mat foundations. And the final thing is, how do you implement this, for this segment at least, is how do you implement this in structural analysis software? Well, again, you simply would input your model for your mat foundation, a layer of springs, another layer of springs, tension membrane, your special springs at the edge of the model. And you can see here how my colleague Horvath-Colasanti did this about a decade ago. Now, he happened to be using version 11 of ANSYS. I'm not promoting ANSYS. This happened to be a program that Regis was using at his employer at the time. So this was the structural analysis program that his employer used, and he was very familiar with, had decades of experience with. And but you see the specific types of elements that he chose. Again, here's two references where he elaborates on why he chose these elements. These are elements that I'm sure you could find in other structural analysis packages that you might have. And yes, I am aware of the fact there are newer versions of ANSYS, but again, this is work that he and I did about 10 years ago. So this was the older version and we used at the time. So my point is this happens to be how this was applied to this particular version of this particular program. But the elements that were chosen and why they were chosen, you could do this with many, many other types of commercially available structural engineering packages that you as a structural engineer may be more familiar with and use in your routine practice or research. So, these are not unique. This happens to be how we implemented it in one particular package. Well, I now want to move on and talk about some case histories, because up till now, this has been a lot of theoretical stuff. It's very nice and all that. I'm sure you're thinking, but is this usable? Well, I've tried to show you it's usable, but say proverbially the proof is in the pudding. I would like to show you how this was actually applied after the fact, granted, to 4 actual mat foundation case histories. And I want to illustrate how you could go out there today, tomorrow, and actually use the things I've shown you on real projects. So this is not just pie in the sky research or hypothetical thinking. These are very usable techniques in actual practice and research. Here's the list of topics I'll be talking about in this segment. After some introductory comments, I'll be getting into 4 different case histories. I'll be presenting 4 mat foundation case histories from 3 different sites within the continental US. I want to illustrate the typical outcomes using the aforementioned MTH method that I developed, that I use for determining both the depth H to an effective rigid base as well as the equivalent single-valued elastic parameters E and G for actual real-world subsurface profiles, and to show you how the Horvath-Colasanti Reissner Hybrid Subgrade Model was implemented into commercially available structural analysis software that, as I said, I feel is typical of state-of-the-practice software that's available worldwide to both design professionals and academicians. I mean, there was nothing unique about the version 11 of ANSYS that was used a decade ago to perform some of these analyses. Now, there are actual mat settlements measured in all 4 of these case histories, so fortunately that provides some ground truth for comparison to the calculated results. But there are some very significant caveats, as I'll point out in a minute. First of all, if you want more details about the first 3 case histories, you can find them in this reference I'll give you at the end of the presentation. And I do want to point out that all of these case histories are based on journal and conference papers published by others. So obviously there were significant constraints on the information that was available to me to work with. Also, the geotechnical information in these case histories was obtained in the 1960s through the 1990s timeframe. And while it turns out the information was adequate for the analyses I'm going to show you, it's not indicative of what we could do nowadays. Nowadays we get much better information with current state-of-the-practice technology. Unfortunately, the structural analyses that could be done were quite crude and simplistic, and that's because in these papers that were used as the reference, very little detail was given about the actual building superstructures. I mean, there were some general, how long, how wide, how tall, but beyond that, no details about these are the columns and, this is what the columns were made out of, etc. So what could be done structurally with the mats, other than the mat, was very, very crude. We just basically assumed some superstructural loads of constant magnitude. So all of the real-world interaction between the structural frame, the mat, and the subgrade could not be modeled. And as a result, there are some shortcomings. I do think that the order of magnitude of the total settlements that were calculated certainly were correct, and I think will be shown to be correct when I compare them to the actual measurements. But I think the differential settlements were inaccurate to varying amounts because of the inability to truly model the real structural mat and subgrade interaction that was going on. So you just need to keep some of these limitations in mind when you look at some of the comparisons that are presented subsequently. Well, the first case history I call the Georgia State University Building B. Very interesting building, originally built in the 1990s for the Summer Olympics in Atlanta, Georgia. Was later a dormitory for Georgia State University and has since changed hands to Georgia Tech, now called the North Avenue Apartments Complex. You see the building here, relatively narrow compared to its length, with brick exterior cladding, or curtain wall as it would be called here in the United States. For the original case history, this was published in a paper by Paul Main, Professor Paul Main, in 2005. You can find that online. Probably the most noteworthy thing in this case history is that it really had a serviceability failure during construction, in that it settled about 5 times greater than what the original designers had forecast due to some computational errors made by the original designers. But interestingly, they were able to finish the building, and it was been occupied ever since for the intended purposes. The actual building footprint, as I said, it was rectangular, was used in all analyses. There was no information about the building superstructure, so in all cases, everybody assumed, everybody meaning Paul Main in his original paper, as well as in the analyses that I performed, assumed a uniformly loaded mat. Main assumed the mat was perfectly flexible, as you'll see in the analyses that I performed with Reissner-Hybrid. We did look at mat stiffness a bit. In terms of the subsurface materials that govern settlements, these are residual soils, and they're typical of what is called the Piedmont physiographic province in the eastern United States. As you see, runs from Philadelphia, Pennsylvania, down here into Alabama. Here's a site in Atlanta here, down near the southern end of this province. And this represents mostly metamorphic rocks that have been heavily weathered and have been unaffected by Pleistocene glaciation. That's why you don't see this Piedmont province continue farther north along the east coast. The Pleistocene glaciation ended pretty much here through the greater New York City area. In fact, the whole reason Long Island here exists is because of the glaciers. So the Pleistocene glaciers kind of cut across the United States in this way. And obviously they removed any of the remnants of this heavily weathered material that exists farther south. Now, although these are residual soils, if you want to look at them From a soil gradation perspective, these are predominantly silty fine sands, sandy silts, and they do exhibit some time-dependent behavior. You see here some SPTN values from Maine's paper, groundwater level. See, the mat foundation is very shallow. This building did not appear to have any below ground space. The elastic moduli were estimated using dilatometer soundings. The dilatometer works well in this type of material, and you see that Maine interpreted the dilatometer Young's modulus to be constant with depth. In the analyses that I performed with Horvath-Colasanti about a decade ago, we used this constant Young's modulus so we could compare results with Maine better. Maine used a closed form theory of elasticity solution. If I were to do over it again, I'd probably also look at a linear increase in modulus with depth. I think one could fit a straight line through these data to find a slight trend of increasing modulus with depth. I don't think in this case it would have a lot of impact on the outcome, though. Now, this was a case where there was no obvious depth to a rigid base. As if you're familiar with residual soils, they kind of transition. You don't have hard defined strata as you do with sedimentary deposits. So they transition from residual soil to weathered rock and then hard sound bedrock, which in this case was something like 40 to 80 feet, 12 to 24 meters below grade. I independently estimated the depth to an effective rigid base using the MTH method, and this came out to be, in this case, about 20 meters or 66 feet. And this is where it plots up on the Berland and Burbidge plot of data they found, as well as their empirical correlation. I think it fits pretty well, actually. If we look at some of the calculated results, this first set of results, an obvious question is, well, how does this hybrid subgrade model compare to more exact models? And because we were just looking at a uniformly loaded rectangular area, we were not modeling the superstructure. We could look at some more advanced models. So we meaning Reissner-Hybrid and I performed a finite element analysis of the subgrade using ANSYS version 11. Also a proprietary layered elastic program called G183 that Reissner-Hybrid had written some years ago. The bottom line is, except at the corners, there was very good agreement. And this gave us some high degree of confidence in the hybrid subgrade model results. Now, I do want to point out that in this case, normally when you have, say, a rectangular mat, you'll see people will present the settlements as either transverse or longitudinal cross sections. In this case, Maine chose to show the data as diagonals in two directions. So that's why we did our analyses plots in diagonals across the mat, which is kind of not standard. So we didn't pick up with the hybrid subgrade model, did not do too well with the corner settlements, but we knew that going in. That's a result of some of the approximations of the boundary condition springs that we used. Of course, the more interesting comparison is to the actual settlements. Here's the actual settlement data you see with the yellow and green triangles for the two diagonals. The blue curves are the hybrid subgrade models. The solid curve is we made an approximation of the mat stiffness, considering both concrete creep as well as crack section behavior. And we also assumed a perfectly flexible mat as Maine had done. It does not make a big difference in this case. Very gratifying to see that there's a very good match of matching the total maximum settlement, which was about 10 inches or 250 millimeters. And by the way, these red stars you see here, this is the original settlement estimate made by the original geotechnical consultants on the project, about 2 inches or 50 millimeters. So as I said, they were off by a factor of about 5, and that's why they had a lot of problems with cracking and whatnot during construction. So the bottom line conclusion is that given all the approximations that went into things, the hybrid subgrade model did a pretty good job, I feel, of matching the actual behavior. Now I want to look at the first of 2 case histories at MIT. The first one being the Whitaker Laboratory for Life Sciences. In the present day, this is known as the Whitaker Building or Building 56. The original case history details are found in this paper by D. Simone and Gould I noted earlier in the presentation. This building was designed in the 1960s during the slide rule era. And really the most noteworthy thing about this case history and the paper written by D. Simone and Gould is that it is a really superb illustration of the correct interpretation of Terzaghis 1955 paper. D. Simone and Gould really understood what Terzaghi was talking about. They only used the Fuss-Winker hypothesis, beam on elastic foundation solutions to calculate local moments in the mat only. They did not use it for settlement analysis. So I really recommend reading this paper to see how Terzaghi's paper was to be interpreted, because most of the papers you've seen ever since are incorrect on that issue. The actual rectangular footprint of the mat was used in all analyses. Now in this case, D. Simone and Gould did make an estimate of the column load, so we're able to do analyses a little bit more exact loading, although we could not model the interaction structure. This here transverse and longitudinal cross sections through the building. You see 2 basements going about 30 feet, 9 meters below grade. Several stories. This was a reinforced concrete frame. I want to call attention to the below ground space here. This is the mat foundation, and the exterior below grade walls were quite thick, about 2 feet, 600 millimeters thick. Reinforced concrete, and the reinforcing was tied into the edges of the mat. So there was a full moment connection structurally, so that really the below grade section acted as a 30-foot deep box beam in the longitudinal direction. So it's kind of interesting, although this was a very rectangular mat, there was almost no differential settlement in the longitudinal direction, because in a sense, in the longitudinal direction, it was almost as if you had a beam that was 30 feet deep, very, very stiff, deep beam, by virtue of the way that everything was connected structurally. So all of the differential settlement occurred in the transverse direction. The subsurface materials are the well-known Boston blue clay you see here. These elevations are all in feet, by the way. And this building was designed as what you see called a compensated mat foundation, meaning the overall average load from the structure, dead weight plus live load, was more or less exactly the overburden stress of the material, 30 feet or so of the material that was excavated. So this was done intentionally so that the Boston blue clay would be loaded entirely within its reload range. Because the nature of the Boston blue clay, as a lot of these Pleistocene era sediments, has desiccation near the top, so it's very stiff and heavily over-consolidated near the top, but then trends to normally consolidated with depth. So in order to minimize settlements, they had to have a compensated mat foundation so that all the Boston blue clay was simply loaded in the reload range, not the virgin curve range, where the settlements would have been anywhere from 5 to 10 times greater had that been the case. The analyses I did were based on the odometer data presented in the paper. This was based on project-specific data as well as some local Boston experience that was published in the D. Simone and Gould paper. So using this, I estimated drain-constrained moduli, then converted them with elastic theory to elastic moduli. I then divided up the Boston blue clay into layers 5 feet thick, 1.5 meters thick, and calculated operative values of Young's modulus for each of these artificial layers. So this is how I developed my artificial layer scheme that I showed you previously. And again, if you were just looking at the soil profile, you would interpret this interface between the Boston blue clay and the underlying relatively dense glacial outwash and till as being a rigid base. But I independently ran the MTH program to calculate the rigid base as well. And I found in this case, the rigid base was calculated to be within a foot or two of the strata change. And you see that here's the effective rigid depth plotted up on the Berlin-Burbage plot, updated. Again, fits in pretty well with the other data. Here's the Georgia State University Building B we looked at previously, and here's the new piece of data. So you see it all fits together pretty nicely, actually. So this was a case where I'm trying to illustrate here that you simply use the soil properties at hand. You come up with an artificial layered system, estimate the operative value of Young's modulus for each layer, and then you use, in this case, I use what I call the MTH method. I think is a pretty good method for this purpose to estimate the equivalent depth to a rigid base as well as single value elastic properties. In terms of calculated results, I'll only show you the comparison with the measured values. We did two analyses. The solid blue curve is no mat weight. The dash curve is with mat weight. And you see the no mat weight correlates pretty good with the measured settlements. I think the reason we get this good correlation is because they only established the settlement points on the mat in the basement after the mat was poured and some of the basement walls were erected. So I think the soils had reconsolidated under the weight of the mat, which is why the better correlation here was with no mat weight. Now, one of the pluses of using an advanced multi-parameter model is now the coefficient of subgrade reaction is no longer assumed. All right? By using a multi-parameter model, you now restore subgrade reaction and the coefficient of subgrade reaction to their original generic roles as calculated outcomes. That's a very important thing to understand. By using a multi-parameter model, by inherently incorporating this spring coupling, this vertical shearing and the real subgrade, you no longer have to guess at what the spring coefficient is. It comes out of the problem automatically. So in this case, here's the subgrade reaction P. Notice now in this case, it's a calculated result. I didn't have to assume this. And the same thing with the coefficient of subgrade reaction. All right? The program calculated the subgrade reaction, calculated the settlement. So if you will, this is the variation in the spring stiffness beneath this mat. Obviously not uniform, but we would have guessed that going in. So this is a very important point to again emphasize. One of the many, many benefits of using a multi-parameter subgrade model is that everything is restored to its generic self. You get subgrade reaction, you get the coefficient of subgrade reaction as calculated outcomes. You don't have to assume or guess these things beforehand. The other MIT case history is the chemistry building. It's now called the Dreyfus building or building 18. Again, another relatively long and slender rectangle. building of modest height. It was designed and built contemporaneously with the Whittaker Lab in the 1960s. Also was discussed in the DeSimone and Gould paper. Here's the loads that they gave in their paper. The interesting feature of this building is that it has very open space layout in the above ground portion for laboratories. So as you can see, most of the column loads were placed near the edges of the mat. The center column load was relatively modest. And here again you see the transverse longitudinal sections through the building. Again, about a 30-foot deep basement, 9 meters deep, compensated mat foundation bearing on the Boston blue clay. And again, the exterior walls, full moment connection to the mat, restraining the rotation at the edges of the mat, providing a very stiff substructure in the longitudinal direction, virtually no differential settlements in this direction. All the differential settlements were in the transverse direction. And you see here the very open floor plan of the above grade space, obviously for laboratory purposes. So the same basic geotechnical data is for the Whittaker Lab, which is very nearby. Now in this case, the variable thickness of the Boston blue clay along the length of the building produced a very, very, very slight rigid body tilt. Very, very small fraction of an inch, 1 or 2 millimeters, very, very small in this direction. Well, again, if we went through the same process of calculating the depth to an effective rigid base, single valued E, and here's the results we see for the chemistry building compared to the Whittaker Lab and to the Georgia State building. All, again, very, very consistent with all these data. And again, a comparison, calculated results, no mat weight and mat weight with the measured results. Now in this case, with the measured results, some of the values that DeSimone and Gould showed, they extrapolated. These were not measured. That's why they're shown by just an unfilled triangle. But admittedly, there is not a very good correlation with the differential settlement. The total settlements were matched, I think, reasonably well. Could be a lot of reasons here. It could be the fact that the interaction with the unusual superstructure framing did not provide a good picture in the calculations. And again, we could take advantage of the fact that with the multi-parameter subgrade models, we calculate subgrade reaction and we calculate the coefficient of subgrade reaction. We don't have to guess at these parameters as you do when you use the Fuss-Winkler subgrade model. Well, the last case history I want to talk about is called the First American Bank Building. This was originally built in the 1980s in Tysons Corner, Virginia. This is suburban Virginia near Washington, D.C. It's now known as the Pinnacle Towers North Tower. This is the building in an earlier age. Maine wrote about this, Professor Paul Maine wrote a case history paper only last year about this case history, which is why it is not included in any of my publications to date. This is the first time in this presentation, by the way, that I am talking about this case history, because as you can see, the data were only published last year. And the footprint of the mat is unusual. The other mats I've shown you had a nice rectangular footprint. This had a very irregular footprint. You see the mat was about 4.5 feet thick, so a little bit more than 1 meter thick. Again, no information about the superstructure, so a uniformly loaded mat was assumed. And because of the irregular shape of the mat foundation, that left a lot of judgment as to how to model the geometry in any after-the-fact analysis. Now, in his 2019 paper, Main assumed an equivalent circular area. He was using a closed-form theory of elasticity solution in his paper. My colleague Horvath-Colasanti did some analyses last year, and he used both an equivalent circle as well as an actual mat geometry in his proprietary layered elastic program, G183, that he wrote some years ago. And I will talk about how you can obtain a copy of this program at the end of this presentation. Interestingly enough, the subsurface materials were very similar to the Georgia site. Here's Tyson's Corner, Virginia up here at the northern end of the Piedmont province. And here's the Georgia State case history down here. So kind of interesting that we're looking at the two ends of this Piedmont province and residual soils. Now at the Tyson's Corner site, FAB building site, these were more of a sandy silt gradation, a little bit finer. Now in this case, Main only had access to SPTN values. He did not have direct access to dilatometer readings, but he used a correlation between SPTN values and dilatometer modulus that you see here. That's based on a number of actual sites as well as actual building performance. And in this site, he came up with this estimate of the Young's modulus profile. You see the blue dotted data. And in this case, there was a very pronounced increase in modulus with depth. So Main used a linear increasing modulus in his interpretation. Well, this is actually kind of interesting because, first of all, now when we look at the hybrid subgrade model, we can do two things. We could say, okay, I've got a number of layers, and I did this very recently for this presentation. I could say, okay, I'll go back to the original data, not Main's linear interpolation. I'll go back to the original data, break this up into layers, in this case, 10 feet, roughly 3 meters thick. I'll divide this up into a layered elastic system with a constant Young's modulus for each of these artificial layers, and I'll come up with an equivalent single value Young's modulus. Or I could use the solution I developed back in the 1970s for the Reissner simplified continuum with a modulus that increases linearly with depth. So this is kind of an interesting case history that there's actually two ways I could approximate the hybrid subgrade model parameters based on the available geotechnical data. And I'll show you the results for both cases in a minute. But first of all, as with the Atlanta site, with these residual soils, there's no obvious depth age to a rigid base. Now in this case, Main reported that the sound rock was about 150 feet, so about 45 meters below the ground surface. So much deeper than in the Atlanta site, where it was 20 to maybe 12 to 24 meters, 40 to 80 feet below the ground surface. So I estimated the H over B ratio, again using the MTH method, and you see the result here. And again, matches very nicely with a trend shown for the two MIT sites as well as the Georgia State site in Atlanta. I calculated the equivalent single-valued elastic parameters based using both the MTH method as well as the Fraser or Mortal method I mentioned previously. It gave very similar results. So again, this is the single-valued Young's modulus, assuming that I have multiple artificial layers, each layer with a constant value Young's modulus. That's how I came up with this number. And of course, once you have this, you can estimate the shear modulus. So you have E, you have G, you have H, you have everything you need to calculate the spring constants in the tension membrane for your structural analysis. Well, in terms of the calculated results, a little bit more, not quite as simple here. First of all, the mat had an irregular footprint, as I mentioned previously. Second of all, the survey measurements were made at irregular points, so it really doesn't lend itself to transverse and longitudinal profiles as you normally see for settlements, or even diagonal profiles as Maine used for the Georgia State Building B. Now, Maine provided data for 5 of these points, the ones highlighted in yellow. So these are the measured settlements that he reported. As you can see, about 3 inches, 75 millimeters near the center of the mat. And again, this is based on these are the actual measured settlements based on the actual measured mat loading. A little bit less, maybe 2 inches, 50 millimeters near the edge. So as I said, I did 2 analyses in this case. First of all, I did an analysis assuming a single constant value, Young's modulus, equivalent, Young's modulus, single valued shear modulus, and I calculated a maximum settlement of about 3.2 inches at the center and 2.3 inches at the edge. Now, in my analysis, I assumed an equivalent rectangle, 140 feet by 150 feet in my analysis. So a pretty good match. I mean, this, considering all the approximations, I think this matches the center and edge settlements pretty well. But as I said, this was an interesting case history for me because it allowed me to look at the solution for the Reissner simplified continuum with a Young's modulus that increases linearly with depth. And in this case, I used Maine's interpretation. And you see the results here, a little bit different. So by using the linearly varying E and G to get the hybrid model parameters, right, 2.9 inches versus 3.2, 2.1 versus 2.3. So a little bit different. But again, considering all the approximations, etc., I think a pretty good match. So I think the bottom line is that certainly in most practical cases, when you're trying to come up with the hybrid model parameters, it's probably going to be better to simply divide the actual strata into artificial layers, estimate a constant E for each layer, and then come up with a constant E for the overall system. However, if you have a case where you feel that Young's modulus clearly varies linearly with depth, or if it varies with the square root of depth, then there are exact solutions available. As I said, these have only been published to date in my 1979 dissertation, but there are exact solutions to date to calculate the hybrid model parameters. So this is kind of an interesting case history to do that comparison. Well, this has been certainly a long presentation. It's kind of hard for me. I've been working on this since 1973, so it's kind of hard for me to take 47 years worth of experience and try to boil this down into not quite 200 slides and several hours of a presentation. So let me try to wrap this up now. Well, we come to the end of our journey here. Let me try to summarize what I feel the high points I've been trying to make throughout this presentation. There are many foundation applications where we need to consider both the force equilibrium and displacement compatibility between a structure and the ground in contact with the structure. Experience just indicates we need to do this if we expect to get an accurate assessment of how the overall structure subgrade system behaves. And these are what I call soil structure interaction applications, and I've used the very classic example of a mat-supported building throughout this presentation to make these points. Now, there's no doubt we've made tremendous advances and continue to make tremendous advances in three-dimensional numerical modeling using the matrix and finite element methods. However, I think doing this, what I call ideal analysis for, say, a mat-supported building, really is not practical, certainly as a sole analytical tool or even the primary analytical tool for routine practice. What that means is in this day and age, in 2020, in the 21st century, there still is a very compelling need for efficient, accurate, alternative analytical approaches to soil structure interaction applications that are based on subgrade modeling and the use of subgrade models. And nowadays, these must be multi-parameter subgrade models. The use of subgrade modeling strategies of breaking things into three components and using the Fuss-Winkler subgrade model that were defensible in a pre-computer era have not been defensible for decades. Yes, that I realize that there are a number of pragmatic reasons why the profession has been slow to change, but hopefully in this presentation I've shown you that it certainly is within any engineer's reach nowadays on any project to rationally apply multi-parameter models based on modern site characterization methodologies and currently available structural analysis software. Again, the real shortcoming of the traditional way of doing things with the Fuss-Winkler hypothesis is that it does not model subgrade behavior properly. As I said early on, we know that subgrade models are inherently approximate, but they must capture the key elements of behavior. And for, say, a mat foundation, the key elements are settlement, as well as vertical shearing within the subgrade to produce load transfer beyond a point of a loaded area. These are essential. And this is simply not possible with a Fuss-Winkler hypothesis. It lacks what we call spring coupling, the inherent shearing that occurs within a. So when using the Fuss-Winkler hypothesis, as most people continue to do, this requires the end user to, in a sense, know the answers to the problem beforehand so you can figure out the correct input parameters so you can calculate the correct answer. And if this sounds ridiculous, it is. Now, yes, we've been able to do this in a few select applications, such as laterally loaded deep foundations, where as the result of decades of research, we've been able to develop reliable PY curves for use in analysis. But this is a very rare specialized exception where we've been able to do this successfully in routine practice. So as a result of this lack of spring coupling in the Fuss-Winkler hypothesis, unfortunately there have been generations of foundation engineers that have wasted their time and money looking for a fundamental soil property that doesn't exist. All right, this mythical soil spring constant is not a fundamental soil property. Never was, never will be. It is, as I've called it, the unicorn of foundation engineering. And it's about time, I think, that we abandon. So I think given the tools that are available to us today, it's reasonable to require the use of multi-parameter subgrade models that take into account that the effective depth to a rigid subgrade is a function of the width of the foundation element. The 4 case histories that I showed you today, I think I've shown you that there are rational analytical techniques that produce results that really fit the general observations of many different researchers. We need to incorporate shearing and spring coupling in the mathematical formulation so that we don't have to resort to gimmicks such as pseudo coupling. We need to basically restore the coefficient of subgrade reaction to being a calculated outcome and not an input parameter that we need to guess at beforehand. And we need to produce one set of displacements. And this would be settlement of a mat in the mat application. The idea that there's separate settlements for structural analysis versus geotechnical simply is not defensible anymore. I feel that the concept of hybrid subgrade models does away with all the excuses people have had of, well, yeah, I'd love to use a mechanical subgrade model, but how do I guess at the spring or the shear layer or the tension membrane? Or I want to use Reissner simplified continuum, but gee, how do I input that into ANSYS or some other structural program? Well, we eliminate those constraints with hybrid models. With hybrid models, we come up with rational ways to quantify these spring layers and tension membranes that are very easy to model in structural analysis programs. But the bottom line still is that accurate subgrade properties are essential. I mean, it is a long-known fact in all aspects of geotechnical and foundation engineering, not just soil structure action, that the quality of the subsurface parameters is the more important than anything else. This recent magazine article really hit the nail on the head when they said bad input and bad equals bad output. There is, no matter how sophisticated the analysis, finite element method, finite difference method, whatever method you want to use, matrix analysis, it will never make up for poor geotechnical data. You need to do a good state-of-the-art or state-of-the-practice site characterization assessment. I'd like to really acknowledge the contributions of Horvath-Colasanti with gratitude. He is very experienced and expert as a structural engineer and has used state-of-the-art commercially available structural analysis software for decades. And really over the last decade or so, it was his collaboration with me that really allowed the hybrid subgrade model concept to be brought into reality. The hybrid subgrade model was something I had thought of decades ago, but it was, quite honestly, I didn't have the analytical experience with using structural analysis software. So I've been very fortunate to be able to collaborate with Regis to be able to show how this can be done. And certainly that was crucial to the case histories I've shown you in this presentation. I do want to point out that Mr. Colasanti's published work is available on ResearchGate. He did perform his own assessments of the first American bank building case history. You'll find that on ResearchGate as well. And he has very generously made available his an executable copy of his proprietary software package called G183 that performs an exact analysis of a layered elastic system. Here are the references, some of the references that I cited in particular throughout this presentation. You could halt the presentation at your convenience and look these up if you would like to get copies. And finally, with that, I want to say thank you for your time listening to this extended presentation. If you're interested in things I've talked about, I would suggest that you get a copy of this monograph that I published in 2018. It contains details on how, not only for the case histories, that some of the case histories I presented, but also gives you details on how to use this MTH method for evaluating H and E and G in actual applications. Also talks about in detail Mr. Colasanti's rationale for how he picks certain elements in structural analysis, things like that. This monograph is available print on demand from any bookseller worldwide. All you need is this ISBN number, and you will be able to get it. And with that, I again say thank you for your time and interest, and I bring this presentation to a close.